All right, I think we can start. Hi, everyone. Welcome to the tutorial, RSS tutorial on Certifiable Robot Perception from Global Optimization to Safer Robots. I'm Luca Carlone. I'm assistant professor at MIT, and I'm one of the co-organizers of the workshop, together with Tat-Jun, who's associate professor at the University of Adelaide, Anders Eriksson, associate professor at the University of Queensland, and Heng Yang, who is PhD candidate at MIT. So before starting, I want to thank you for tuning in to this workshop. I hope that you and your loved ones are doing well, and also wanted to thank two of our co-organizers who are tuning in from Australia, and for them it's essentially midnight at this point. So let's get started. So this meeting actually started, the idea of organizing this tutorial started from another meeting, which was in January 2019. It's called the Shonan meeting. So the Shonan meeting is a particular format in which essentially researchers come together in small groups to have focused and intensive discussions about specific topics. And in this case, TJ in 2019 organized the Shonan meeting on optimization methods in geometric vision, discussing what is the role, for example, questions such as what is the role of geometric vision for computer vision applications, including self-driving, UAVs, robotics, and so on. Understanding what properties differentiate geometric vision problems from other optimization problems, and understanding how hard it is essentially to solve geometric vision problems. So through this meeting, we realized that there is a lot to be done in this area, and it's really an area which is at the boundary between multiple research fields, including computer vision and robotics. So after this meeting in January 2019, we organized a previous event, which is kind of a twin event compared to this RSS tutorial. So the previous event was an ICCV tutorial in October 2019, which was called Global Optimization for Geometric Understanding with Provable Guarantees. At ICCV in Seoul, in Korea, we got around 200 participants. You may remember these nice times in which conferences were in person, and you were going other places to enjoy the conference with your colleagues. But I guess the message here is that the topic we're going to discuss this morning is of broad interest across multiple research communities. And indeed, you'll find papers dealing with global optimization, certifiable perception with global guarantees in many venues across robotics, computer vision. I'm listing here RSS, ICRA, IROS, CVPR on the computer vision side, CVPR, ICCV, ECCV. And not only, you will find papers along this research line also in applied math venues and across multiple communities. So what is the topic of today's tutorial? Today we want to talk about certifiable perception, and we want to stress the importance of certifiable perception for safe robots. So why do we care about perception? Well, it turns out that you should not be surprised that perception right now is a great moment for robotics in general, but also perception technologies are essentially playing a huge role in many robotics applications. Here I'm showing a couple of very relevant examples. On the left, you see the self-driving car, the Tesla autopilot, and you can see that there is in this demo, which at this point is a few years old, you can see that there is a lot of computer vision and perception going on. You can kind of understand that there is some object detection, there is some lane detection, road detection, and also I think in some of the images there were some features that were tracked. And the same, you can look at other applications like drones, for example, and perception is playing an important role for drone in enabling obstacle avoidance and navigation in unknown environments. While perception is positioned to be a very important technology for the future of robots, the broad adoption of this technology is also showcasing fundamental limits of the algorithms that you are working on right now. And in particular, the message that I want to give here is that perception algorithms are increasingly used for safety critical applications, such as self-driving cars. And in this application, failures of the algorithm can have catastrophic consequences. So here is an accident from a Tesla from a couple of years ago in which the vision system misdetected this concrete obstacle on the left of the car and decided to turn into it, killing the passenger. And these are other examples of failure of well-engineered systems, such as Google Earth, in which you can see that even like engineered system will have failure modes in which the reconstruction of a bridge in this case is completely off. So message so far is that certifiable perception in general is important, and doing it right is even more important for safety critical application. And this brings me to the goal of this tutorial. So the goals we have are these four that I'm listing here. We want to connect practical performance of perception algorithm and provable guarantees of these algorithms, including accuracy and robustness, to ideas that go back to global optimization. We want to review basic mathematical tools. This is supposed to be a tutorial. We want to review basic mathematical tools for global optimization, and in particular, convex and semi-definite relaxations. So we are going to start with a review of basics of optimization, and we're going to work out a simple example. I'm saying simple, but actually a pretty advanced robotics example. We want to offer you a survey of recent advances on the use of relaxation in vision and robotics, and we want to outline open research direction. All the research that we're going to discuss has been booming in the last few years. There is plenty of work to do, and we want to make sure that as you walk out from this tutorial, you have some good idea about the open research directions, spanning from theoretical contribution that you can make in your future to even applying these technologies. The plan for this morning is as follows. We are right now in the middle of the introduction here, and we're going to have 4 presentations. The presentation around 35 minutes, and there is a little bit of a break of 10 minutes after each presentation. We're going to be flexible, so if you guys have a lot of questions, you can take a little bit of the break time to answer more questions. And the 4 presentations are essentially trying to cover to sample this space, which is this idea of certifiable algorithms, and it's going to sample this space to give you an overview of different aspects of interest. Anders is going to start with the first presentation. He's going to talk a little bit about history, but mostly is going to cover the notion of optimality and how that impacts performance in robotics and vision application. And the key role of the first presentation is just to give you the basic concepts about optimization, which we are going to mention again and again in the other talks. I'm going to give the second presentation. In the second presentation, we're going to jump on the use of, focus on the use of convex relaxations for robotics. And I'm going to work out an example, which is related to simultaneous localization and mapping in robotics. I'm going to show you that despite the name, relaxations can be often exact, can not entail any approximation. We can develop fast solvers, and I will review a bunch of cases in which our groups and other researchers in the community were able to develop successful relaxations in geometric perception. TJ is going to talk about another important aspects in real-world application, which is robustness to outliers. Outliers will always be present in robotics and computer vision, and is going to stress very fundamental results about intractability of geometric perception with outliers. And Heng is going to close the tutorial with some very recent idea about how to successfully use convex relaxation for perception with outliers. So before we start, I have one final slide here, which is giving you a little bit of the rules of engagement for this morning. First of all, we want you to ask as many questions and interact as much as you want. There are 2 main ways to do that. At this point, you're most likely connecting from the RSS portal, so you should see in front of you an interface like this. You will see 2 buttons. One is stream and the other one is engage. Right now you're looking at me, so most likely you're on the stream tab. And inside the stream tab, you should see an interface which is essentially Zoom. And within Zoom, there are two ways that we suggest using to ask questions. The first one is just use the chat. You can write your question in the chat and we are going to monitor that. The other one is that if you click under participants, there should be a function which is called raise hand. And we're going to monitor that as well. If you raise your hand, we're going to call on you for asking the question directly. The other approach, so these are the two approaches that you can use. There is another approach, which is clicking on the Engage tab on the RSS portal. If you click on the Engage tab, you're going to see Slido, which is just this interface in which you have a tab essentially in which you can type any question you have. And you can also decide whether the question is anonymous or whether you want to put your name next to the question. The breaks, as I mentioned, we're mostly going to stay online for the breaks. Feel free to stay online as well. Feel free to ask questions and to tell us about the problems that you care about. As we go, we're going to release more and more online resources. Right now, you're going to find already plenty of online resources at the SCCV tutorial from last year, as well as on the website of this RSS tutorial. And these resources include some material. We're going to release slides. We're going to release a little bit of code, references listing pretty much all the approaches that we're going to cover in this tutorial, proposed in both vision and robotics, and not only, I would say. So with this, I would say that we can get started. And I just wanted to see if there are any more comments from the other organizers. Otherwise, we'll get started with Anders.
Yeah, I'm ready. Let's see. You can see that okay, I hope? Mm-hmm. Me too. Okay, well, first of all, good morning, everyone. Well, not really. It's just past midnight down here in Australia, so me and TJ might be struggling a little bit, not yawning. Anyway, so yes, my name is Anders Eriksson. I'm an associate professor at the University of Queensland here in Brisbane. And my talk is going to be, well, the aim of it is to try and give I guess a gentle introduction to global optimization, but the topics that I'm going to be touching on specifically are the ones relating to convex relaxation and a concept known as duality or strong duality. So the motivation behind this talk, and I guess this whole entire line of research relates to the fact that robotic perception or robotic vision or computer vision or whatever you want to call it, it's something that concerns itself with understanding the world through images, with a wide range of different applications. So here, for instance, you can see we have the problem of 3D reconstruction. We have something like image understanding. On the bottom left, we have an example of 6 degree of freedom pose estimation, perhaps. In the middle there, robotic localization and mapping and SLAM, and perhaps something like image segmentation or semantic image segmentation. But what is common is that these problems typically leads to some form of an optimization problem. In the first one there, 3D reconstruction, you look at minimizing some form of reprojection error. In the image understanding task, you look at perhaps learning through minimizing some related loss function in training. The pose estimation problem might be formulated as minimizing some form of model fitting error, geometric errors in the SLAM example, for instance, and so on. And what is also common is that in a majority of these applications, this resulting optimization problem is highly complex. Non-convex formulations typically that are very difficult to solve globally. So typically what you do in these settings is that you pick some starting point and you start moving downhill until you can't any longer. And that is then the solution to your problem, or at least you hope so. The issue with this approach of this steepest descent minimization type approaches is that you can rarely be certain of the quality of the resulting solution. So in this image here, if you have that approach, you don't really know which of these two local minimas you've ended up in, or one is the global one that you want and one is a local one that is not desirable. Here you can see some examples of what the difference between local and global solutions might look like. This is the task of post-graph-based SLAM in 3D. And each column here denotes different local optima each row, different local optima. Each column here is a different problem. The first three columns are simulated settings, and the two rightmost ones are from real applications. And the true one is the one at the bottom. So as you can see, they differ quite drastically. And as Luca mentioned, the consequences of failing to distinguish between a local minima and a global minima can be quite significant, from comical to very serious and potentially lethal outcomes. So in this talk then, my aim here is to, like I said, to give a bit of an introduction to global optimization, hopefully a gentle one. I'm going to talk about a couple common approaches to solving these problems. The three ones I'm going to discuss is a method called branch and bound. I'm going to discuss a little bit about an approach called prompt loop formulation or construction. And then I'm going to spend perhaps a majority of the time talking about relaxation, convex relaxation, and duality, and then end up with just showing a couple of example applications. But before we get going, I thought I'd start a bit easy by quickly going through the necessary basics, just to so we're on the same page. It's early for you guys, perhaps, and it's late for me. So I'm just quickly going to go over these three. Just mathematical optimization, what is it, and how do we define it? Then talk a little bit about convexity. It's a very, very important concept in optimization. And lastly, I'm going to introduce the concept of relaxation. So the first one, mathematical optimization or optimization. What do we mean when we say that? Well, one way of defining it is to say that it's a task of choosing the best option among a set of alternatives. So what do we mean by best? Well, that's typically measured by some form of objective function. This might be some error that we want to minimize, or some loss function that we want to minimize. But it's this is described by the objective function. Then the alternatives are described by constraints. This is what limits your choice in how you can choose. These are typically given in a number of different ways. You can be given, you can have them as inequality constraints, equality constraints, perhaps some kind of set notation. It depends a little bit on the problem and the author of that paper. It's not entirely consistent annotation here, but normally when you define an optimization problem, you write it like this. So you minimize your objective function, ST or such that, these list your constraints. And again, these can be given as inequality constraints, equality constraints, or with some form of set notation. You often talk about optimization as always minimizing things. This is not always consistent again, but sometimes it might be more intuitive to say that you want to maximize something. You want to maximize some kind, perhaps maximize some energy or maximize some form of some measure of similarity. But you can always rewrite the maximization problem as a minimization problem. They're equivalent in this sense that maximizing f of x is equivalent to minimizing minus f of x. Lastly, this problem here, or the problem that we want to solve, is sometimes called the primal problem, also denoted by capital P. Next, we have convexity. And this is perhaps one of the most important concepts in optimization, much more so than, say, linear versus nonlinear. This is really a famous quote by a mathematician called Terry Rockefeller, saying something like that: the great watershed in optimization is in between linearity and nonlinearity, but convexity and non-convexity. So when you talk about convexity, you can sort of talk about convexity in two different ways, with two different meanings perhaps. The first one is you talk about convex functions. A convex function is a function that is well behaved, doesn't have any only has one single minima, and that's the global minima. Like you see on the left here, a non-convex function is a little bit more messy. The formal definition of a convex function is that if you pick 2 points on the curve of the function, the line segment that you draw between those 2 points will always be above or on the function itself. So this is true for here on the convex function on the left, but it's not necessarily true for the non-convex function. You also sometimes talk about concave functions. The definition of that is basically f of x is concave if minus f of x is convex. So sometimes you use these two terms a little bit inconsistently perhaps, but sometimes you talk about minimizing a convex function, and sometimes you talk about maximizing concave functions, but they sort of have the same property because you can turn one into the other. The second concept in convexity is that of convex sets. Has a similar definition. So you can here see the convex sets. The convex set is the one on the left, and the non-convex one is a set on the right. And the definition is that if you pick any 2 points in the set, any line segment you draw between the two needs to be completely within the set as well. So that holds for the convex set on the left, but not for the non-convex set on the right. So when it comes to optimization, it turns out that having a convex objective function is not enough. The constraints must also define a convex set. So we put these pieces together. It means that if you have a convex objective function over a convex set, it's called a convex problem. And these are very, very nice problems to have. It turns out they're easy to solve. No local minimas. You're always guaranteed to find the global optima. In fact, it turns out that if you solve a convex problem and you find a local minima, it's also always the global minima. And again, maximizing concave function and minimizing convex function are sometimes used interchangeably. So then the third concept, that of relaxation. The idea here is basically that if your problem is too difficult, just try to replace it with a simpler one. More formally, perhaps, it's an approximation of a difficult problem by a nearby problem that is easier to solve. So, for example, if we want to solve this problem here on the left, that's the problem we want to solve. That's a primal problem, but for some reason it's too difficult. Perhaps let's assume that the constraints are particularly difficult to deal with here. One approach we can have is just replace the constraints. Replace them with constraints that are more manageable, and in this case denoted uppercase h of x. Or if you want to, you can just drop the constraints altogether. That results in a relaxed version of your original problem. So for these, in this setting, it's important to note that the solution of the relaxed problem will always be less than or equal to the solution of the original one. That's important to remember, because we're going to get back to that. Of course, a requirement for that to work is that when you do your relaxation, your relaxed set is bigger than the original one, and it contains the original constraint set as well. But as long as you do that, the relaxed problem will always be less or equal less than or equal to the solution of the regional one. So that is it. Those are the basics. And we're now ready to start talking about global optimization. And as I mentioned before, I'm going to go through 3 different concepts. The first one is an algorithm called branching bound. The second one is this approach of problem construction. And the third one is using something called convex relaxation. So starting with the branching bound. So this is a very classical method in global optimization. It's been around for a while. It first introduced back in the 60s. It's also a very general algorithm. You can find global solutions to discrete, combinatorial, as well as continuous optimization problems. And it's quite simple. It's a quite simple idea, but it's quite a clever one at the same time. And it's not too difficult to understand what's happening. So let's, for example, say we want to find the global minima of this clearly non-convex function over some interval. Here the interval is shown in yellow. Now, instead of, and we assume that this problem is difficult to solve. This is quite a trivial illustration of it. But the idea here is to find a lower bounding function to this blue function, ideally a convex one, or one that's easy to solve, and solve that one instead, and then build on from there. So it might look something like this. This is our original objective function. We still have the same interval. Let's say somehow we're given this lower bounding function. This is a much easier one. As you can see, it's convex. And we solve that one instead. And if we do that, we might end up finding the minimum, which is down here somewhere. Again, we know since this is a lower bounding function, this will give us a lower bound on the global optima. We can also evaluate the original objective function at the same point. That gives us that function value. So by doing this now, we've now found an upper bound and a lower bound on the global optima. We know that the global optima has to be somewhere in between those two. So what we then do is that we take our original interval and we split it, or we branch it. We divide the problem into smaller subproblems. Here we use 2 intervals, so we split it into a left part and a right part. And then we'll repeat the first step again. We do that individually for each of the subproblems. So if we look at the left interval, we find this lower bounding function, and we solve that. And then we also evaluate the function, the original function at the same point. And then we do the same thing for the right side of the interval. We solve, or we minimize the lower bounding function instead. We also, again, for the right interval, we get a lower bound and an upper bound. Now, if you take another look at this, especially if we're starting on the left interval, you can make the following observation: that the lower bound we get on the left interval is higher than the upper bound we got on the previous step, when we did the bounding on the entire interval. If you think about that a little bit more, that means as well that the global optima cannot be in that left interval. And we can actually remove it altogether. We can focus our efforts on the right interval. On the right-hand side, you can't do the same. You can't exclude it, because the bounds that we get are in between the old bounds. But what you can do, since we know now that that we discarded the left side of the interval, we can now update the bounds. We now get tighter bounds on where the global optima lies. And then the idea is that you do that. Those are the only 2 steps you do. You bound and you branch. And you keep doing that until you manage to eliminate and discard enough intervals, or that the difference between the upper and lower bound is small enough and within some desired tolerance. and then you stop. And that's essentially the idea behind this approach. You do this, it's sort of a clever way of doing your state-based search. The only thing that it requires, and I didn't really touch on too much, is that it requires this tight convex bounding function. It's some technical details around it with on the properties of such a function. Exactly how to find that function is not entirely trivial. It depends highly on the problem and the setting. But if you manage to find such a function, you can apply branch and bound. And there are some standard methods you can try to do this. And the good side with this is that it works for a very, very wide variety of problems. The downside of it is that it can be quite slow and often becomes impractically slow for more than a handful of dimensions. But it's worth mentioning, it's one of the more famous methods for doing global optimization. The second approach to global optimization is the one of problem construction. And this essentially, idea behind this one is that just construct your problem, formulate it in such a way that it can be solved globally. Unfortunately, this is not always that difficult, and it's not always possible. It requires, I suppose, a fair bit of experience in optimization and convex optimization and global optimization. It also limits what you can model. And also you have to make concessions, you have to make trade-offs. You have to exclude certain things from your problem formulation in order to be able to compute to solve the resulting problem globally. And an example of this, perhaps the most well-known example from at least from the computer vision community, is that of the L infinity or the max norm methods. The idea here is if you want to solve certain problems in multi-view geometry, it turns out, and this has been shown, that if you choose the norm that you use, the norm on the residuals, if you choose that carefully, the problem is in fact solvable globally. There are no local minimas in such problems. And the norm that you normally would use in this situation is the L2 norm, but that has been shown to be non-convex, and it's also resulting in many local minimas. So here on the bottom here, you can see this an example of 3-view triangulation. So here we have 3 cameras. This is in 2D, U1, U2, and U3, with known positions and known image points, and you want to find what 3D point gave rise to these images. And you can then go on to show that if we measure those errors in the reprojection area using the L2 norm, the landscape, in this case is a 2D landscape, looks something like this. We have 3 local minimas. But if you instead change the L2 norm over to the L infinity norm, it turns out that problem only has 1 global minimum. So this is all good, I suppose, but here the trade-off or the concession that you have to make is that you're now dealing with a norm that is known to be very, very sensitive to outliers. So that's the price you have to pay here. But this is perhaps a good example of where you construct your problem from the get-go to be one that you can solve globally. Then the next one, I'm going to spend perhaps most of my time on, is that of convex relaxation. The idea here is, again, similar to that of relaxation that I mentioned before, is that you have some original problem. Here, our primal problem P, that for some reason it's too difficult to solve globally. We'll then try and find some relaxed problem, ideally convex, and we'll solve that instead. Now, in general, an approach like this normally only provides approximate solution to the original problem. But it's a misconception that this approach is always approximate. It turns out that in certain situations, convex relaxation such as this can provably solve the original problem exactly. And at the center of many such relaxation and their associated proofs is a concept of Lagrangian duality. And because of this, I'm going to try and take a few moments and explain Lagrangian duality in a bit more detail. And since Lagrangian duality can be somewhat abstract concept, the aim is mainly to be towards giving an intuitive understanding of what it is and how it works. And it turns out that all the concepts we need to understand Lagrangian duality are the ones that we just went through in the preliminaries a few slides back. So the background of Lagrangian duality, it's a well-known concept. It's a well-established theory on duality, especially relating to convex optimization problems. Duality is at the core of most existing optimization algorithms. But less is understood about the non-convex case. There's a few notable exceptions to this. And it can be viewed as being based on the concept of relaxation. And to try and illustrate that, we're going to start off with looking at this problem here. So again, this is our setting. Let's say this is the problem that we want to solve. I'm just going to use equality constraints for simplicity. You can do exactly the same thing using inequality constraints as well. It just makes the notation a little bit messier. So again, let's say we have this problem. It's difficult to solve, and let's further assume that the issues we have with this are that the constraints are making it difficult. So what we can do is do what we did before. Using relaxation, we just say, well, okay, well, let's just remove the constraints and solve that resulting problem. And the assumption here again is that if we do that, we can solve this relaxed problem much more easily, and we can solve it globally. Now the downside here is that's probably not a very good thing to do, but let's do it anyway. So let's say we have the following situation. This is sort of an attempt to illustrate the problem. Where here the blue curve is supposed to represent our primal problem, and the red curve is supposed to represent the relaxed problem, the problem on the right. Now, this notation here isn't entirely technically correct, since our primal problem involves constraints, and the blue curve, there are no constraints involved there. But again, this is mainly aimed at trying to provide an sort of an intuitive picture of what's going on here. So let's say we do this. We relax our problem and we solve this, and we solve the red one, we solve the relaxed problem, we arrive at that solution there. It's not great, but it's not too bad either, I suppose. So what else can we do? Well, we can do the following thing. We can take our original problem and we can add h of x to the objective function. We can add the constraints to the objective function. Since h of x is always 0, we haven't really changed anything. The problem is still the same problem. If we manage to find a global solution to that problem, it still will be the same. We haven't made things any easier by doing that. But the observation that we should make here is that the relaxation we get by removing the constraints is now a different one. And if we do the same thing, we solve this relaxed problem, we'll get a slightly different one. So if we solve this one, we might look something like this, and we arrive at a slightly different relaxed solution. We can do the same thing. We can add, or something similar, we can add 2 times h of x to the objective, relax that, and we arrive at yet another relaxed version of our original problem. And we can solve that and arrive at yet another solution. In fact, you can do this for any multiple of the constraint function that you want. And if you do that for a whole range of relaxation, where you denote different values that you multiply h of x with by lambda, it might look something like this. So depending on the lambdas, you get a whole suite or a whole family of relaxed solutions. Now, again, if you recall from the slide on relaxation, is that since we're viewing this, what we're doing as a form of relaxation, we also know that the resulting problems will always be underestimator, so lower bounds on the original problem. So we know it doesn't matter which lambda we put in there, the resulting solution will always be a lower bound than the original one. Now, the natural next question would then be to ask ourselves, what lambda gives us the best underestimator? So which lambda gives the largest value of this expression here? So we want to maximize the minimization of f of x plus lambda h of x. Now, some of these terms in this expression are so common that they've given them names. The first part, the f of x plus lambda h of x, is denoted normally by L, and it's also called the Lagrangian or the Lagrangian function. The minimization with respect to x of the Lagrangian function is called the dual function, denoted g of lambda. Again, this is a function of lambda now. Yes, and that leads to sort of the following image, I suppose. Where we have a Lagrangian, we have a dual function, and we try different values of lambda and solve those functions, and the situation looks something like this. You remove the red bits, maybe something like that. And this is then what is called the dual problem, to finding the best underestimator, to maximize the dual function, or that is the dual problem, to maximize the dual function, to maximize g of lambda, to find the best underestimator of our original problem. And again, since this dual problem is a relaxation, we have that the optimal value of the primal problem is always greater than or equal to the optimal solution of the dual problem. What's also interesting is that, as you saw, the dual function here is shown as a concave function. And that's not by accident. It turns out you can actually show that g of lambda is always a concave function. Even if the original problem is not a convex problem, the dual function will always be a concave one. And maximizing a concave function is something that we can do efficiently and do it globally. And again, like I said before, you can generalize this to also include inequalities. Now, this still only provides lower bounds to the original problem. So a natural question then is to ask, how good of an underestimator is then the dual problem? The difference between the solution of the primal, B star, and the solution of the dual, D star, is called the duality gap. And it might look something like this. In our problem it did. But sometimes this happens, that P star and D star coincides. So P star is equal to D star, and the duality gap is 0. When that happens, we say that strong duality holds. And again, there's a lot of established theory, has been for a long time, on how and when this happens. But for example, strong duality always holds if the primal problem is a convex problem. There's some technical details around that, but in general, that's true. But strong duality is not guaranteed to hold for non-convex problems, with a few notable exceptions. So just a quick summary of Lagrangian duality. Yeah, and that is essentially it. That is the idea behind Lagrangian duality. And to just quickly summarize it, it's based on the idea of relaxation. The dual problem can be interpreted as looking for the best possible relaxation. The dual problem is always convex, so it's easy to solve. But it only provides a lower bound to the original primal problem. But it does provide a systemized way to construct tight convex relaxations to non-convex optimization problems. In addition to that, if we have strong duality, if we can show that that property holds, that it then also allows us to solve non-convex problems with guarantees on global optimality. And you can find such solutions and do it efficiently. So why is this then relevant? Again, like I said in the beginning of the talk, that most of the problems that we're looking at in perception or vision lead to complex optimization problems once they're difficult to solve. But if we can establish this property of strong duality, at least in some form, we gain a lot. And I guess the most important one is that if that holds true, we're always guaranteed to find a global solution to that problem. We don't have to worry about initialization. It might affect sort of runtime, but as far as global optimality goes, it's not important. And you can also solve the resulting problem efficiently. And at the moment, there are two ways, I suppose, to try and incorporate duality, or more essentially strong duality in robotic vision and computer vision. One is called verification or certification of solutions. The other one, sufficient conditions for strong duality. An example of the first one is this problem here. It's called generalized 3D registration. Here you want to register two 3D shapes with each other. You want to find the rotation and the translation that aligns them as well as possible. And you do it in such a way that it does not only involve points, but it might also involve lines and planes. That problem itself, you want to solve something that looks a little bit like this. You can formulate that as a quadratically constrained quadratic program, denoted QCQP. It can easily be shown that those, especially in this case, that is a non-convex problem. And what they do in this example is that they relax this using semi-definite program and kind of solve the dual and hope for the best. Well, not hope for the best, but they solve it anyway. And once they find the global solution to the dual problem, then you can try and construct a feasible primal solution from that dual solution. And if you then manage to show that the duality gap between those two solutions is 0, then you don't have to do anything more. You basically certify that the solution that I have is the global one. There is no better solution. So there's two papers here that are referenced to. One is from Briales et al. And one is from Yang and Carlone, published only a few months ago, I think. And then the second example, here is the problem of rotation averaging. This is the problem of determining absolute camera rotations from pairwise relative measurements. So here we have, for example, four cameras, and we know their relative rotations, and we now want to find what are their absolute rotations, at least up to some global world reference system. And similarly here, you can show that the primal problem is can be written as it is done on the left here. And the associated dual problem looks like that. It's a semi-definite problem as well. But for this problem, you manage to show something slightly different. You can actually show beforehand. You don't have to check each individual solution, but you can actually try and provide sufficient conditions for when strong dualities always will hold. So in this case, you can actually show that if the noise levels are sufficiently small, strong duality will always hold, which means that if that is true, if those noise measurements are small enough, you can solve the dual problem, and you're guaranteed to always find the global minima. You don't have to check anything. You don't have to verify anything. Yeah, and that's basically it for my talk. I think I went over a little bit on time, so I might just finish there. See if there are any questions.
Thanks. Great presentation. Very, very clear. I think we have a question about. So, what's the use of moving into the dual view if it is guaranteed to find a global minimum only for convex problems, for which we can already use existing solver? So I guess the question is, how should we use the dual in non-convex? Why do we care about duals in non-convex problems?
Well, I guess you can. It all comes down to if you're able to show that this property of strong duality holds, it essentially gives you the answer. So it is guaranteed to hold for for convex problems, and again, but for non-convex ones, it's not entirely clear. But it is a tool that can be used to verify your solutions or show that the solutions that we give are always the global ones. Did that make sense? That was a very good answer, I think.
I would make that statement even stronger. I would say that the reason why we are so concerned about strong duality in this tutorial is that indeed many non-convex problems showing up in geometric perception, they have strong duality. They are non-convex, but they have strong duality.
Yes, yeah.
And to make that statement a little bit more precise, they have strong duality typically when the noise in the measurements is not huge, in the sense that, at some point strong duality will break, but the important thing is that it breaks in a setup which is too extreme to show up in practice.
Yes, yeah. No, I definitely agree with that. I mean, to me as well, what I find interesting with it provides a very formalized way of answering the question of is my solution the global one, and then exactly what approach you take around it, if you do it either as a sort of a certification approach after the fact, or if you try to say something even before you start the optimization. I guess that depends on the problem itself and how amenable they are to each of those approaches.
Cool. There was another question before, which I think was partially answered by TJ in the chat, but I think Maulin was trying to get a little bit more insight about why the L infinity norm was a better choice. Like, why you got convexity or you get a unique global minimum if you have the L infinity norm.
It turns out if you really dig in under the hood and look at the very deep into the mathematics, it turns out that if you do this, if this function, you can still see my sharing right here. So you want to minimize these residuals, and these. It turns out that this term here is something called a pseudo-convex function, and it turns out that the maximum of a number of pseudo-convex functions is still pseudo-convex, but unfortunately, the sum of squares of pseudo-convex functions is not pseudo-convex. That's the thing that differs the two.
Interesting. Very interesting. Okay. So at this point, I think we have our 10 minutes break became a 2 minutes break. So I suggest that, well, there is another question. So I think let's take the other question and we'll do without the break. So the other question is, Lagrangian duality seems to be a particular way of constructing convex relaxation. Is there proof that the resulting relaxation is the best you can get?
Yes, there is. You can show that the convex relaxation you get using duality is the tightest one. So it's the one it's the best possible convex relaxation of that particular problem.
Cool. I think I will have.
Don't know the reference of the top of my head.
I think I will show an example exactly of that and the relation between Lagrangian duality and more traditional view of convex relaxation in my talk as well.
Yeah.
Thanks, Anders. At this point, there should be a standing ovation or something. Unfortunately, with Zoom, we cannot do that. But thank you so much for the talk.
Yeah. Thanks for your time. Thanks for listening.
I think it's pretty much time to start directly with the second talk. I will try like to stay like, and to make sure that there is a break after this talk. The talk is supposed to be 35 minutes, and let me start. Okay. So, hi again, everyone. And as I mentioned, I'm Luca Carlone, I'm assistant professor at MIT. With this second presentation, I want to essentially leverage the basic notion that Anders gave us in the first talk and try to show how to apply this in practice. I will consider examples which are practical, they are robotics examples, so they are directly applicable to your research in SLAM and so on. But at the same time, they're easy enough to just showcase how easy is in some cases applying this notion of convex relaxation, duality, and so on. So the goal of the presentation is to show that in many of these robotics problems, in particular, I'm going to talk about SLAM, these relaxations are exact. So in the words of Anders, there is strong duality for these applications. And if you get lucky enough, you can also design very fast solvers for these specific problems. And I will conclude with a few pointers to other applications which are still close to robotics and computer vision, in which the same is true. Strong duality holds. Most of this presentation is about problems without outliers, in which essentially you have some least squares cost. And I think the following presentation will focus on problems with outliers. So let me just say, like, I'm Luca Carlone, I'm the director of the Spark Lab. In my lab, in general, we are doing robotics research, and we are particularly concerned about perception for robotics. This is one slide overview of the work we do before we enter in the details of like, the topic of this talk. So in the past, we've been working. Okay, so we're working a lot on robust perception, localization, and mapping, and this idea of certifiable algorithms. We are going to hear a lot about these today in this tutorial. We are also concerned about problems which are a little bit farther, like, a little bit away from the topic of this tutorial, including high-level scene understanding and metric semantic reconstruction, and other topics which are even, like, away from perception, including processing networks and drone manipulation. So the truth is that I started this investigation as a student, and at the time I was working a lot on SLAM, simultaneous localization and mapping. And we're going to try to use for this talk, we're going to use SLAM as a running example to show how easy it is to use this idea of relaxations. So these are two examples of SLAM that we have worked on over the last few years. This is back 2017, is visual inertial navigation, in which you fuse information from cameras, inertial sensor to build 3D reconstruction of the environment and an estimate of the trajectory of the robot that you see in red here. And this is a more recent example. This is about cave exploration, is about LiDAR-based SLAM in the context of the DARPA Subterranean Challenge. So this is a project we're involved in right now. We just won the competition, the DARPA Subterranean Challenge, the second event of the competition, which was last February. But for the sake of this presentation, the message I want to give in this slide is that despite the apparent complexity of these SLAM problems, there are complex sensor data, LiDAR, cameras, inertial measurements. The basic message is that SLAM at the very core is solving an optimization problem. And this optimization problem in its most common form is about using sensor data to figure out the trajectory of the robot, okay? So in SLAM, the robot is moving in a completely unknown environment, and what you want to do is to process sensor data to figure out its own trajectory, the trajectory from time 0 to the current location of the robot. And typically after you figure out the trajectory, it's fairly easy to do a 3D reconstruction of the environment, which is the mapping part. So the optimization problem showing up in SLAM is typically called, one of the most popular, which we're going to look at today, is post-graph optimization. I'm going to tell you in the next slide what this is about. And in its more general form, it's called factor graph optimization, which is slightly more general. So what is post-graph optimization? Again, like, we want to, in SLAM, we want to figure out the trajectory of the robot given sensor data. The basic idea behind modern SLAM system is to abstract away this problem into a simpler one, or, like, abstract away the sensor measurement and move from the original problem of the robot, model the original problem of the robot moving in the unknown environment as a graph, okay? So here you want to estimate the trajectory of the robot. The basic idea is to model the trajectory as nodes in a graph. So T1 is the pose at time 1, T2 is the pose at time 2, and that's exactly what you want to reconstruct, the poses of the robot over time. And in this graph, the edges corresponds to measurements within two poses, okay? So there is, for example, an odometric measurement between pose T1 and T2, because we're able to measure the odometry between the two poses. And in general, it's true that every edge in this graph is obtained by some pre-processing of the sensor data. So there is something that is called the SLAM front end, which is going to pre-process the sensor data to create these edges in the graph. So on the mathematical side, we abstracted away a very complicated problem into a very nice and simple mathematical formulation in which essentially we want to estimate poses attached to nodes in a graph. So these are the T1, T2, T3, and so on. And remember that each pose by definition is just a rotation, Ri, and a position Pi. And what we are given to solve these poses are relative measurements attached to the edges of this graph. So we are given this Tij bar, which is a measurement of the relative pose between node I and j, in this case between node 6 and node 2. And these relative poses attached to each edge are again relative poses. So there is a rotation component, Rij, and a position component, Pij. So geometrically, for example, for this edge, the measurement is a measurement of the pose of this guy, T4, with respect to the pose of T3. So this is what is called a pose graph. And there is actually a fairly established way to compute the poses attached to the nodes of this graph, which is indeed called pose graph optimization. And not surprisingly for this tutorial, is an optimization problem. So just to reassure you that this is a fairly popular tool, this is what you will find at some point in the backend of OrbSlam. This is what you will find in the backend of direct methods for SLAM, like optimizing the entire pose graph after you do loop closures. And this is implemented in very popular libraries, including G2O, GTSM, and so on. So what is this optimization problem? This optimization problem looks a little bit complicated. So I will tell you like all the details about it. But essentially what we are trying to do in this optimization problem is to try to figure out the unknown position and the unknown rotations of the robot. And remember that we have many of those. So we have one for each node in the graph. So we are sampling these poses along the trajectory of the robot. And we are computing this position and rotation in a way that minimizes this cost. And the cost function at the high level is just penalizing the mismatch between the pose estimates and the corresponding measurements. So this is particularly easy to see in the second term here. So you can see that we are trying to find the rotation at node I and j such that the relative rotation between I and j is as close as possible to the measurement Rij bar. And there is some norm, which is the Frobenius norm, is essentially like, just measuring the distance between these two rotations. And there is potentially, if you want, you can set this to 1, but in general, there is a weighting term. The sigma is just a known weight, which is measuring how certain you are about this measurement. So the sigma will be large if your measurement has a lot of noise. The sigma will be small if your measurement is very accurate. And the first part is doing kind of the same for the position part. We are trying to figure out positions, Pi and Pj, such that you match as well as possible the measured relative position Pij. Since the relative position Pij is in a local reference frame, you have to rotate it by Ri. Okay, and you have a bunch of measurements, one for each edge in the graph. So you have potentially a large set of measurements. And again, the quantities with the bar are the measurements attached to the edges in this graph. So I started, when I was even a student, I started looking at these problems, and I was kind of frustrated because the state of the art was about using local solvers. And the basic idea of local solvers is that they kind of worked in the sense that, you were able to get like decent performance, but not the robustness that you really wanted from these kind of systems. Local solver is about, as Anders was saying, it was about starting from an initial guess and going downhill. You can think about iterative solver being some sort of gradient descent, which is starting from an initial guess and trying to go down here in the cost function. The video here is an example of a gradient descent applied to a post-graph optimization problem in which the poses are sampled along a sphere. You can see that we start from an initial guess, hopefully we converge and we converge to a good solution. In this case, we converge to a nice solution. The issue with the post-graph optimization is that, again, this is a non-convex problem. So if you initialize this local solver close to the global minimum, you get a very nice estimate. In this case, you get a nice reconstruction of the trajectory of a robot moving in a parking lot. But if you initialize your local method with a bad initial guess, you get a suboptimal estimate, which typically corresponds to a very wrong trajectory reconstruction. So in other words, the issue is that iterative solvers are brittle, might converge to bad solution if the initial guess is not accurate. One thing that is worth mentioning is that in many of the problems that we're going to discuss, including SLAM, it's possible to design a minimal solver. So a minimal solver is a solver which is taking just a subset of the measurements and is trying to estimate the quantities you care about, in this case, the poses, starting just from this subset of measurements. So here I'm saying that in many cases, one can solve the optimization problem easily, given a minimum number of measurements. And that is definitely true for SLAM. So if instead of considering all the edges in the graph, I just consider a path, as in this case, or I consider a spanning tree, it's trivial to compute the poses. I can just chain the measurements and I can obtain an estimate of the poses. But the issue with this approach, which is actually indeed very popular in computer vision, is that these kind of minimal solvers produce poor solutions in the presence of noise because indeed they are neglecting most of the measurements. So the topic of this tutorial really is about addressing fundamental question, which is, can we design optimization techniques that, first of all, do not require initial guess, which is a source of brittleness. Second, that work with an arbitrary number of measurements. We don't want to use a subset of the measurements. We want to use all of them. And third, we want to design a technique that, that is guaranteed to compute a global solution, okay? So the answer to this, of course, is yes, we can do this. And the result is what we call, what have been called in general, certifiable algorithms, certifiably optimal, certifiably correct algorithms. In computer vision, they're also called non-minimal solvers. And the basic idea is essentially algorithms that are performing global optimization. So I want to give you an example of certifiable algorithm in this presentation. And I will spend some time, actually most of the presentation, on the first part, which is about telling you that getting a relaxation in many problems is actually easy, okay? And I will show how to get an SDP relaxation, a semi-definite relaxation for SLAM for the case without outliers. And following talks are going to focus on the case with outliers. I'm going to touch on the fact that if you get lucky, solving a relaxation can be indeed fast to solve, okay? And I will have 2 or 3 slides with extra application in which you can replicate the same derivation to get relaxation for other problems. So let's start with relaxation with relaxing is easy. Okay, we're going to start looking at post-graph optimization, but actually I will start with a problem which is slightly easier than post-graph optimization. I will show you that by simplifying the problem a little bit, I will go back to post-graph optimization. Later on, I will show you that you don't miss anything, okay? So we start with a simpler problem, which I will show eventually is the same as solving post-graph optimization. So what I want to do is that instead of solving these, which is a little bit scary if you look at it, I want to solve just the second part of it. So I want to solve just the rotation part. So I'm moving from post-graph optimization to something that is called rotation synchronization. So these 2 problems are the same, except I gave up on the first part and I gave up on solving for the positions, PI. So I'm just solving for the rotations in a way that is minimizing the mismatch with respect to the rotation measurements Rij bar. And again, I will go back to the fact that rotation synchronization is general enough, later on will allow us to solve even post-graph optimization. So this is kind of nice and simple, right? There is a quadratic cost function. There is some constraint here. We can manipulate this a little bit to make it even more elegant. So we can realize that I can rewrite this term, Rj minus Ri, Rij bar, as the product of two matrices. So one, which is the R, in which I'm stacking all the unknown rotations I have in my problem. Okay, so this is 3 by 3n. And I just multiply with a known matrix, which is just including the measurements and some identity. And just by multiplying these two, you can see that you can get exactly this term. So if we can write each one of these terms as a product of a rotation by a constant matrix, it shouldn't be surprising that, you know, if you massage a math a little bit, we can reformulate exactly this optimization problem as a problem with a quadratic objective. Okay, so everything is function of R, which is this stacking of rotation matrices. We can reformulate rotation synchronization as a problem with a quadratic objective in quadratic equality constraints, which is what Anders called the QCQP, a quadratically constrained quadratic program. So again, the objective here is just applying this trick to each term in the sum, and you get a quadratic term. And there is also a constraint. And on the constraint, to make sure that you guys are still there, I want to just try real quick if I can poll you guys about, you know, what you think about essentially where the constraints are coming from. So at this point, you should see a poll in front of you, and I'm going to call on Anders, Heng to confirm that they're seeing the poll. And I will ask you guys to take a look at the poll and try to reply. The poll is essentially asking, where do the constraints in this optimization problem come from? And I will give you a few seconds to answer that. We have a few votes coming in. All right. You guys are still there. That's good to see. All right. So let's give maybe 10 more seconds, okay? And again, if you're not sure, just answer not sure is still a good bit of information.
Excuse me, how do we access the poll?
You should see it just on your screen. And I see responses, so many of you are seeing the poll. Unfortunately, if you don't see it, it's probably a glitch in Zoom, so don't worry about it at this point.
Luca, I think the problem is if they're using the embedded Zoom client, then they won't see the poll.
Okay, so I guess that the people I see here are just opening Zoom on their side. Okay, let me end it. I think it's still a good exercise. I can read you the answer. So the question is where the constraint Ri transpose Ri equal to the identity come from? Sorry. And there are different questions here, but essentially the basic answer that most of the people replying got correctly is that essentially here we're starting with a problem which seems unconstrained, but actually there is a constraint hidden here. So we are not looking for any matrix Ri. Let me stop sharing the poll. All right. Okay, so back to the slides. The basic idea is that in this optimization problem, we do have a constraint, which is the rotation matrix is a member of SO3, which is the set of 3D rotations. And the set SO3 is defined as the matrices, which are 3 by 3, which are orthogonal, so satisfy R transpose R equal to the identity, and have determinant +1. So this is exactly where the constraint here comes from. I'm just enforcing each rotation to be orthogonal, which is each rotation should be like, you know, a rotation. And something that is important noticing is that I'm dropping the determinant constraint. There is a way to model the determinant constraint within the relaxation. Doesn't help, like, you know, doesn't change much in the relaxation, and it's just a little bit more complicated. So we're going to forget about it, and actually you don't lose anything in performance. So in this slide, what I'm saying is that we're going to consider rotation synchronization as a proxy for SLAM. Rotation synchronization can be written as a very nice and simple problem in which you have a quadratic constraint, the Q bar here is a known matrix, and you have these quadratic equality constraints. And Anders, I think, already mentioned that this is a non-convex problem, okay? So the quadratic cost is fine, this is convex, but the constraints are non-convex because quadratic equality constraints are non-convex. So a lot will be of this presentation will be about how to relax this problem formulation. Quick slide to show that rotation synchronization is actually not a toy example. Indeed, rotation synchronization, which is also called rotation averaging, is a building block of structure from motion in computer vision. It's actually a very important problem. There will be papers in computer vision looking at rotation synchronization. And this is a paper in robotics doing essentially structure from motion and estimating, in the process, estimating the rotation of the cameras through rotation synchronization. Okay, so let's get on how to do a convex relaxation for rotation synchronization. Again, it's called also rotation averaging. And you're going to see that in these slides, actually in 2 steps, I'm going to get the convex relaxation, which is much, much easier than using Lagrangian duality. And then I will show that using Lagrangian duality pretty much is the same, okay? So we start with a heuristic way to design the relaxation, and then we're going to do the formal way using Lagrangian duality. So this is the original problem that we want to solve. Again, this is called the primal problem, and we said that this is non-convex, so it's hard to solve. The basic insight of this problem is that in this problem, if you stare at it, you know, the R, which is the variable, shows up only in the form R transpose R. And if you look at the shape of these matrices, R transpose R, you know, will have this shape in which the rotation matrix is multiplied by itself. I think there are a bunch of transposes missing here, but I think that's fine. And the basic observation is that R transpose R is a square matrix. Okay, after you do this multiplication, you get a square matrix. Moreover, being a multiplication of a matrix by itself will be positive, semi-definite. We'll have all the eigenvalues larger or equal than 0. And also we'll have rank 3, just because it's the product of 3 by 3n matrices. So the basic idea, very easy way to get the convex relaxation here is to say, why don't we replace R transpose R with a square matrix? So let's call this square matrix Z. So if we replace R transpose R with this square matrix, the objective becomes like, you know, essentially a linear objective in Z. At the same time, we have to enforce the fact that Z is equal to this, which we said is the same as enforcing that Z is positive semi-definite and the rank of Z is equal to 3. And if you stare enough at the structure of Z, you realize that Ri transpose Ri are essentially on the diagonal of the Z. So to enforce the same constraint here, Ri transpose Ri equal to the identity, you just have to force that the diagonals of the Zi of the Z matrix is equal to the identity matrix. So you see that here we're just changing variables, right? You're moving from R transpose R to a Z formulation, but these two, we said they are exactly the same, they're equivalent, right? And the nice thing here is that we isolated the non-convexity of the problem because we got an objective function which is linear, that's definitely convex. This is a semi-definite constraint which is convex. The rank constraint is the only thing here that is non-convex, okay? So a heuristic way here to get a convex relaxation is to say, okay, let's take this equivalent formulation, let's drop the rank constraint, and the resulting problem is convex, right? So the objective is the same, the constraints are the same, but we dropped the rank 3 constraint, which was non-convex. So the resulting problem is a convex relaxation, and this is a specific convex problem which is called a semi-definite program because it has constrained like, you know, matrices being positive semi-definite. The nice thing out of this convex SDP relaxation is that it's easy to get a posteriori check. After you solve the convex relaxation, you can check if you indeed got the right solution or not. So it's very easy to get a theorem saying if the solution Z of the convex relaxation has rank 3, then it can be factored into R transpose R and R solve the original non-convex problem exactly, okay? So you can solve the SDP relaxation, check the rank of Z. If you get lucky and you get a rank 3 solution, you essentially are able to solve exactly the same problem. And the nice thing, I'm going to stress that in the next few slides. The nice thing is that in practice, you get often rank 3 solutions out of this, so the relaxation is exact. So this, I said, is a kind of a heuristic way to get a convex relaxation. What about, you know, how can we use instead the theory from Anders about using Lagrangian duality? So Anders said that for any primal problem, we can build a dual problem, which is somehow like, you know, tricky, it looks complicated. While the primal problem is NP-hard, typically for perception problems, the dual is going to be solvable in polynomial time. And Anders also mentioned that under weak duality, the objective of the primal is greater than the objective of the dual. If you get lucky, we have strong duality, and in that case, the objective of the primal and the objective of the dual are matching. So if you try to apply this exercise to rotation averaging, we get that the primal problem is the one that I was showing in the previous slides, is a QCQP, which is non-convex. And if you do the math, you can get also the dual problem, which is this one. So in the previous version of this tutorial, I was doing the derivation of this expression. It actually takes 10 minutes. It's like straightforward, just math. It's just essentially formulating this cost function and showing that the minimization, the inner minimization, can be solved in closed form. So in this specific problem, it's very, very easy, like, to get a dual problem. And the dual problem is a maximization of the dual variable lambda, which is again another matrix, subject to a constraint that this lambda somehow with respect to the data matrix Q bar should be positive semi-definite. So far I showed you two different ways to get relaxations, essentially. Just a heuristic way to get a convex relaxation and Lagrangian duality. And in the next slide, I want to discuss how to use these two things and how they relate to each other, which goes back also to one of the questions we got in the chat during the previous talk. So the first way in which you can get, you can use this idea of duality and relaxations, for example, in rotation averaging, is for optimality certification using the dual problem. I think this was already hinted to by Anders. So let's say that, I have my original problem. I try to use any existing tool to get a solution to this problem. Then I compute the dual problem here, which I can solve in polynomial time. And the basic idea is that when strong duality holds, the dual problem is able to predict the optimal cost of the primal exactly. Okay, so what I can do here is that I call a local solver. The local solver is giving me a local solution to the primal. I can solve the dual to get this optimal objective. And using this optimal objective, I can say, okay, this local solver converges to a wrong solution because it's suboptimal. And instead, if I call again local solver and it obtains the optimal solution, I can essentially verify the optimality of the solution returned by the local solver. Okay, this is what is called optimality certification, or is also called sometimes verification. So this is the way we can use the dual problem. It turns out something that is pretty interesting is that if you have the primal problem and you apply duality, of course, you get the dual problem. If you apply duality to the dual problem, in other words, you get the dual of the dual, you get another problem, which is a convex relaxation, okay? And if you work out the math, it turns out that the dual of the dual problem is exactly the convex relaxation that heuristically we derived in the previous slide, okay? So in other words, the relaxation that you get through Lagrangian duality and the relaxation I got just by manipulating the math are the dual of each other. And since they're both convex, they will give the same optimal solution. They will attain the same optimal cost. So through the convex relaxation, I can have a second use of this convex relaxation. I can essentially solve the convex relaxation and I can try to estimate my variables directly from the solution of the convex relaxation. And again, when strong duality holds, the convex relaxation solves the primal problem exactly. So the reason why we care so much about this relaxation in SLAM is that it turns out that strong duality holds in the problems you care about for rotation averaging, and we are going to see that the same message holds for post-graph optimization. So back in 2015, 2016, we're, for example, looking at the percentage of tests in which the duality gap is 0, which means that strong duality holds, in 2D rotation averaging. And here we're plotting the percentage of cases in which strong duality holds for increasing rotation noise. And you can see that strong duality holds up till the rotation noise is equal to 1 radian standard deviation, which is a noise that you will never find in practice, okay? So essentially in practice, strong duality holds for all the problems you care about in terms of rotation averaging. This was our original empirical observation. Anders and TJ came a couple of years later, CVPR, saying that essentially you can indeed compute a bound on the maximum noise below which strong duality must hold. Okay, I will not read the entire theorem, but the theorem is saying that if the rotation error on the measurements is below this threshold, then strong duality holds, and the threshold essentially depends on the structure of the graph. Okay, the good news is that for fully connected graphs, you can tolerate up to 40 to 60 degrees error on the measurements, and you can still have strong duality, which means that which makes this convex relaxation a very powerful tool. So rotation averaging can be solved through convex relaxation. It turns out that if you go back to SLAM, we can do pretty much the same. And this is the expression of post-graph optimization I was starting from. Again, there is the position part and the rotation part. Already back in 2014, we noticed that the position here appears quadratically in the cost function and is not constrained. Positions are any vectors in R3. So essentially what happens is that for the sake of the position, this is a least square cost, which is easy to solve in closed form. So what you can do is you can solve for the position in closed form and substitute this position back, leading to a problem which is only dependent on the rotation. And indeed, if you do the math, you eliminate the position part, you can end up exactly with the same structure of the rotation averaging problem that we saw in the previous slides, with the only difference is that the Q bar here will have a different structure, okay? Because we'll also include information about the position measurements. So what I'm saying here is that with this formulation, exactly the same convex relaxation that I was showing in the previous slides will apply also to SLAM and post-graph optimization. And the good news is that strong duality will also hold for SLAM. Again, you can try to increase the rotation noise and the translation noise on the SLAM measurements. You can check the percentage of cases in which strong duality holds. And it turns out that for extreme noise, you can still get strong duality. And it is particularly true for 2D SLAM. If you move to 3D SLAM, strong duality breaks a little bit before. So you can see here that I'm plotting the primal optimal objective and the dual for increasing level of noise. And essentially strong duality starts breaking at 0.1 to 0.15 radians, standard deviation on the rotation measurements. It's a big open problem which was partially addressed by the work with David Rosen back in 2016. The problem is about finding a non-trivial noise bound for strong duality. So we said that Anders and TJ, for rotation averaging, they were able to establish this theoretical bound below which strong duality must hold. The same result is not available for post-graph optimization. We cannot quantify what is the maximum noise under which there is strong duality. We have some initial result, again, like, from the work on SC-Sync, but which is saying that essentially strong duality will hold below a beta, but the expression of beta is not something that we are able to give in closed form. So Anders already noticed that actually convex relaxation will make a difference. So if in SLAM you run a local solver like Gauss-Newton and gradient for different data sets, you can get local minima. The convex relaxation will return you a visually correct solution and will also give you an optimality certificate, again, when the solution of this problem is rank 3. Okay, so in the second part of this talk, I want to spend 3 slides commenting on the fact that for specific problems, in particular for SLAM problems, solving this relaxation can be very fast. And I want to spend like a few minutes on that. The typical concern is that, that you can hear after you work a little bit on convex relaxation is that the comment is that semi-definite programs are slow to solve. So they are polynomial time, but they are not as scalable to solve as what you can do, for example, in local solvers. But the truth is that for specific problems, you can indeed engineer a very fast solution for these semi-definite relaxations. So what I said in the first part of the talk is that we transformed, let's say, the rotation synchronization problem into a convex semi-definite relaxation. And if you look back into the literature on convex optimization, it turns out that Buehrer and Montero back in 2003 said that a good way to solve this kind of optimization problems is to replace the Z with a product, x transpose x, and try to solve locally this problem instead, okay? So after you replace z with x transpose x, the positive semi-definite constraint becomes redundant and you remove it, and these constraints can be written as x transpose x. And for those of you who have seen this for the first time, this would sound a little bit crazy because essentially we did a convex relaxation, and then to solve it, we go back to a problem structure which is identical to the first one, right? But here the trick is that the x is a little bit larger. So instead of having 3 rows, we'll have many more rows. We'll have 5, 6 rows. And the insight here is that if this number of rows is large enough, you can prove that a local solver applied to this problem will give you the optimal solution to the SDP relaxation, which is something that I'm trying to formalize in the next slide. So the Buehler-Monteiro method has been known since 2003, but only recently people started to understand that there are theoretical guarantees that you can establish when solving the Buehler-Monteiro method. And in particular, Bumal in 2016 got a very nice result saying that essentially if you solve the Buehler-Monteiro method, you get an X star. This X star is rank deficient and is a second order critical point of this problem. Second order critical point is a condition which is very easy to check. Then X transpose X is a global minimum of 2, okay? So a local solver applied to this problem can find a global solution to this one. And Bumal also said that if the number of rows in this matrix X, if the number of rows is large enough, any second order critical point will be a global minimum of 2, okay? So if you make X large enough, you can try to solve with a local solver this Buehler-Monteiro method, and you will always get a solution to the SDP relaxation. So these insights sparked a number of contributions, and the important bit here is that there exist solvers, Manop is a general solver for this kind of problems in MATLAB, and this work has been pioneered in robotics in particular by David Rosen, who has been working on this library, which is SCSync, which is in MATLAB and C++, is open source, which is a specialized solver for SLAM and rotation averaging based on the Buehler-Monteiro method. So how fast is this Buehler-Monteiro method? Well, indeed, it's pretty impressive if you consider SLAM datasets. Here on the rows, you can see a bunch of SLAM datasets and very large problems, right? Thousands of poses, 10,000 of poses, 30,000 ages, and you look at the cost in terms of time for a local solver, let's say the Gauss-Newton solver, and you compare that with the SCSync, which is based on this idea of Buehler-Monteiro, you can see that a good implementation in SCSync can be even faster than a local solver. And here, not only SCSync is faster, you can see that there is roughly an order of magnitude difference in terms of timing for some of the data sets. Not only that, but SCSync is a global solver, so we'll get to the optimal solution here. All right, so I'm running a little bit out of time, so we'll close with other applications. Here, I really want to mention a few key ideas. I think I have 2 or 3 slides left. The basic idea is that S4SLAM was a success story. We're able, the community was able to design complex relaxation, which are empirically tight, and to develop even fast solvers. We're seeing the same trend in other applications. So for 3D registration, Anders mentioned in his slide that 3D registration is about aligning point clouds, which is a problem showing up for scan matching in robotics or for LiDAR detection in LiDAR-based object detection. And I think Anders already mentioned that there exists a tight relaxation for this problem. And what I want to stress here is that, well, first of all, I'm showing here again the percentage of optimal test for increasing noise. And you can see that the relaxation, which is the blue one, is always tight, always successful. But I want to use this slide to observe a couple of things, okay? So the first observation is that I already mentioned that it is possible to include the determinant constraint, which arises from the rotation matrices as quadratic equality constraints. And I mentioned that that didn't matter in SLAM, but it turns out that for this problem of generalized registration, including that constraint makes a difference. And in particular, there is a general observation that if you had constraints that may be redundant for the primal problem, you may still end up with a better relaxation, okay? So if you add more and more constraints to the primal problem, you can help improve the quality of the relaxation, which is some key idea that shows up in this work on registration and also in the next slide. By the way, this is work from Briales, CVPR 2017. Briales has been doing nice work on tight relaxations without outliers. This one is another example from Briales, CVPR 2018. Is about two-view geometry, which is about estimating the motion of the camera between two timestamps. So the camera is observing a bunch of points projected on the camera itself. And the problem, don't pay too much attention to the math, but the problem is about using these pixel measurements to figure out the position and rotation of the robot up to scale. And Briales again showed that it's possible to get a tight SDP relaxation where the optimality gap is 0, which in other words means a strong duality holds. These are just two examples, but the truth is that in the last, I would say 2 to 3 years, we've seen many examples of cases in which you have geometric perception, in particular geometric perception without outliers. And we can just relax these to typical SDP relaxations, and we have strong duality. One example is object detection in images using lines and points, which is called the PMP with points and lines problem. Again, this is like in Archive 2019. Group from Jonathan Kelly at the University of Toronto have been showing tight relaxation for extrinsic sensor calibration, which is an important problem in robotics. Group of Jonathan Howe at MIT has been working on use of these convex relaxation for SLAM, for distributed multi-robot SLAM. And more recently, there is an increasing emphasis on geometric perception with outliers. I will not talk too much about this because it's essentially the topic of the next two talks. So we'll conclude here, and I will say that for the bottom line of this talk is that for many convex relaxation of geometric perception problems are exact. If you get lucky, you can get even fast solvers for these relaxations. And designing the relaxation is actually a systematic, there is a systematic procedure, which is Lagrangian duality, although sometimes you have to hit, to manipulate the math and add redundant constraints to improve the quality of the relaxation. This is a little bit of an art, although Hank in his talk is going to provide a little bit of a more systematic way to do that. There are clearly a bunch of open problems. So noise bounds for strong duality, currently, this is an open problem for many problems, except for rotation averaging. Deriving exact convex relaxation for other 3D vision problems is largely open. There are still many problems to go. And problems with outliers, again, most of the work on problems with outliers is over the last 2 years, so there is definitely more and more work to do there. So I'm largely out of time here, so we'll finish here. Thank you guys for the attention. If there are questions, I will be happy to take questions. Otherwise, probably we'll have to move we'll take probably a short break and then move to the next presentation. Okay.
I can ask a question if there's time.
Please, yeah. I also see many questions. I don't even know where to start here. So yeah, go ahead, please.
Yeah, so yeah, I posted one question on the chat.
Yeah.
It's pertaining to most of the results that you showed. They seem to be for a batch mode SLAM solution where you have all of the data beforehand. Do you have any insights into how this can be, made adapted for an online or an incremental solution?
It's a good question. I get that question a lot, actually, and I think that there is a trivial question, there is a trivial answer, and there is a deep answer. So the trivial answer is that you can do two things, right? So you can solve at time t, right? You can compute an estimate, and you can use that estimate to warm start the optimization at time t+1. So you can still use an initial guess, and by bootstrapping the convex relaxation with this initial guess, this is going to be faster. Okay, so it's kind of a warm start mechanism. Another potential solution is to realize that in SLAM and in postgraph optimization, you don't need to optimize at each time. Actually, if you do not have loop closure, the optimal solution for SLAM is just to concatenate the odometry, right? So ideally, more than being just batch, this is a solution or a solver that you need to invoke only when you have loop closure. So like every now and then you get a loop closure, and in a separate thread you run this, which is still pretty fast to compute a globally optimal solution. Yet another answer is that you use a local solver most of the time, use GTSM and these existing local solvers, and use this theory in the background to sanity check that the solution from the local solver is optimal, which is this idea of optimality certification. So these are the three immediate ways in which I would deal with incremental operation, online operation in SLAM, manipulating the math in a way that is typically done in incremental SLAM to make this truly incremental and online. I think there is a deeper answer there, and there is investigation to do. So that's open problem, I would say. So just to summarize, there are trivial ways to do that. If you want to get really the maximum speed up and work out the math to get the maximum speed up, it's an open problem.
Yeah, thanks.
So there is a question about determinant constraint that I dropped from the derivation. So I will try to address a bunch of questions at the same time on this determinant constraint. The basic idea is that if you drop the determinant constraint, you can get both rotations and reflections, right? So reflections are typically is not a physical motion of the robot, so you don't want that, you want proper rotations. So what is possible to demonstrate, and I think David has a proof for that in the SCSync paper, is that if the noise is not crazy, like, under all reasonable noise assumption for the rotation measurements, the solution of SCSync will be either all rotations or all reflections. And in the case in which they are all reflections, you can flip the sign. Let's say you can flip the sign of these reflections and you can get the corresponding rotation. Okay, so in other words, you can, a posteriori, you can state that that constraint is redundant for the SLAM problem. It's not true, for example, I mentioned that for registration, for example, is not true. Other problems which are open in 3D vision. So that's another question. Can you give some examples of other open 3D vision problems? I mentioned one area for which you will learn much more in the last presentation, but the truth is that while this work I'm presenting here, SCSync and all these relaxations have been the first to show the power of this relaxation for robot perception, the presentation I just gave and all the relaxation that I've been showing in the previous slide here are without outliers, right? So there are many relaxations without outliers, but the truth is that in practice, you always have outliers. So I think that right now, one of the most promising research areas is to repeat the success of these problems, point and line PMP, extrinsic calibration, distributed multi-robot SLAM in the presence of outliers, okay? So we started working partially on that in the group. You will hear from Henk about that. I think we have very interesting results, but I would say that there is plenty of space there to do new contributions. For example, something that I can be very upfront saying that we do not have a satisfactory solution is SLAM with outliers. So you will see that I'm putting a reference here to Lacroix, et al. 2019, where the initial relaxation for SLAM with outliers is not performing is not as robust as you want for real world problems. So for example, there is more work to do there. If you think about other vision problems, I don't know, I feel that somehow you can, this stuff of convex relaxation can essentially redesign the way we understand vision, the way we understand optimization for vision. So I suspect that if you go back to very traditional problems in vision and geometric vision, multi-view geometry and so on, you can do a lot of new contributions. Let me add one final thought, open problems. So SLAM, I mentioned postgraph optimization as an instantiation of SLAM which we have been successful in solving. But if you think about SLAM, there are many, many more different formulations. There is visual inertial navigation, there is visual SLAM. All of these will have a slightly different mathematical formulation, and all of these will potentially benefit from having, like, you know, a global solver, because you will remove the brittleness that is intrinsic to local solvers that used right now. I think was a like long answer, but I hope that that it added a few bits.
Luca, do you want to look at the question by David Zhang, which is right above money for bundle adjustment?
Okay, so that's great. So that's what I was hinting to. Bundle adjustment. I have to admit that bundle adjustment, I tried looking at the math, I think back in 2016 or 2017. For a reason or another, I decided to focus on the outlier case. I don't think that there is, I think the math is slightly more complicated, because if you do projective geometry, there will be, like, you know, fraction and division by variables, and so will be like rational polynomials and so on, will be a little bit more complicated. And at that time, like, you know, I decided to look more into problems with outliers. My suggestion is to look into this. So I think that right now, for example, what we learned as a community over the last 3 or 4 years, I think that these problems are attackable. Okay, so bundle adjustment is attackable, visual inertial odometry is attackable. And I think if you're interested in that direction, David, listening to the talk from Heng should be particularly useful in understanding like, you know, how tools which are a little bit more advanced than Lagrangian duality can help design these convex relaxations. The warning, you know, that I give you is that remember the point from Anders about, you know, problem construction. So problem construction is fundamental. Not only you have to be clever in designing the convex relaxation, you have to be clever about picking the problem in the first place, picking the formulation in the first place. So something that I didn't mention in this talk, and I was mentioning, for example, back in 2016, is that now we are calling these the standard formulation for post-graph optimization, this one in the slide. But actually, before, like, you know, we proposed this idea of convex relaxation, was very common to use a different error for the angle, for the rotation cost. Okay, so this is called the chordal distance. Many people before 2016 were using the angular distance, which is a little bit of a different mathematical expression. It turns out that, you know, with that formulation, it was kind of very tricky to design a convex relaxation. So my invitation is to be clever about picking the cost function and understanding, typically when you pick a better cost function, there is a motivation for that. So for example, we justify that for a specific choice of noise on the rotation, that's the right cost function. So try to understand what is the most convenient formulation and try to understand how to ground that in terms of assumption on the noise of the measurements. So guys, I'm running super late here, and I think there are more questions, but I will try to address these directly in the chat. At this point, I think is pretty much needed to have a 5-minute break. Maybe let's start actually in 7 minutes at 11:55 with TJ's talk. We are running late, I apologize, I went a little bit long. TJ, in the meanwhile, if you want, feel free to start sharing screen and making sure that everything is fine. We're going to start in 5 minutes sharp. And feel free to take a break if you want.
Should I start now, Luca?
Yeah. Thanks, CJ.
Okay. Thanks everyone for being here. Title of my segment is Outlier Robust Geometric Understanding, or as I call it, the bad news. So this is myself. Everyone calls me TJ. I'm from Adelaide Uni. So you know, it's not surprising, and it has been mentioned a few times before, that outliers invariably exist. This is a problem from a space problem where we're trying to detect orbiting satellites, and they tend to streak because they're orbiting really fast. Tend to streak when they appear in front of the camera. So the task here is to find a line corresponding to the streak amidst you know, a bunch of clutter. And you know, very standard problem in computer vision in 2-view geometry. Given a set of correspondences, feature correspondences computed using a black box method like SIFT or SURF, try to estimate the transformation, a geometric model that you know, aligns them, or you know, underpins this set of correspondences. Some of the correspondences will be wrong because the black box method is not perfect, thereby giving rise to outliers. Luca mentioned scan matching before. In robotics, often we'll want to match 3D point clouds. And again, a black box feature matching algorithm will give you wrong correspondences, which again gives rise to outliers. In postgrads optimization, we have incorrect constraints arising from wrong loop closure detection, for example. So they give rise to incorrect constraints. Which again gives us the outliers in the formulation. Okay, so very quick intro to why we have outliers. Now, how does that change geometric understanding or geometric optimization when we have outliers? Without outliers, normally we want to find an estimate of a model M given a set of data D. And we want to minimize the sum of some error of each data point for a candidate model M. Okay. If we square it, then this tends to be a least squares type of formulation. And R, I forgot to mention, is a residual, or the error. If we have outliers, we want to avoid the outliers from biasing the result of the estimate. So typically, we want to pass the residual or the error through some kind of a robust loss function. So example 1, camera localization, given 2D, 3D correspondences with outliers. We want to find the 6 DOF camera pose, rotation, and translation. Oh, okay, I'm missing the rotation and I'm missing the translation in the domain here, but you know, just imagine that there's a T there. We'll minimize, for example, the reprojection error, and then if there are outliers, we want to pass the reprojection error through a robust loss function. In rotation averaging, we're given a set of relative rotations. We want to estimate a set of absolute rotations using the chordal distance again. But if there are outliers, we don't want to minimize the sum of all the chordal distances. We want to minimize the sum of them being passed through a robust loss function. Okay, so this will be a standard a running example in this segment of the talk. At least it's easy, it's simple. I can draw diagrams easily, and the results can also be more easily motivated. So I want to estimate a simple line X, and this is not even a line with an offset. This is a line that passes through the origin. So really, it's just a direction, AX equals to B, that want to estimate given a bunch of points AI, BI. And the residual would be given by this vertical distance here between a point and a line estimate X. Okay, so ideally, I want to find that line X star. Okay, so in a robust formulation, because as in the previous example, in the previous diagram, I have outliers. I want to pass this vertical error through a robust loss function, rho. And here's a few robust loss functions that have been, you know, proposed in the statistical literature. All right, the ones that I highlight in the blue circles are called the hard redescenders, because as you see, as the error goes further away from 0 up to a point, the loss function rows starts to stay constant. They don't increase anymore. Okay, hence they're called hard redescenders. The hard redescending robust loss functions are non-convex, and that's necessary because we want to absolutely limit. We do not want the outliers to limit we do not want the outliers in any way to bias result of the estimate. So if it's a normal L2 function, if the robust loss function is normal L2 function, then we revert to the normal least squares, which, as we know, is not robust. Okay, so here's a hard redescender. It's called Tukey's byweight, which, yeah, it's the last one here. That's the mathematical formula for it. It's kind of like you can imagine it as some kind of a truncated L2, but it's not really. If you can see the definition here, but you can imagine what it's doing here. It's allowing the inlying points to influence the estimate, but the outlying points after a certain threshold stops influencing the estimate. In computer vision and in robotic vision, we often use this kind of robust loss function. It's simply counting the number of outliers. Okay, so instead of paying attention to how much the error is, we just want to count how many points are within error within the threshold. How many points are outside of the threshold 1 in this case. And this gives rise to what we call the consensus maximization formulation, which is often used in computer vision and robotic vision. So we want to count, given a bunch of points, estimate a model X, but estimate X such that the number of inliers are maximized. Okay, so we find a number of points such that its error with respect to the candidate X is within a threshold epsilon, and this indicator function simply counts them. And that count of inlier is called the consensus of a candidate model X. Okay, so back to our running problem. If given candidate X, this has a low consensus because it doesn't have a lot of inliers in it, and therefore it's not a good fit. What we want to find is this line where it has the most number of outliers. So essentially find a slab epsilon or fixed width epsilon that contains the most number of points within the slab. Okay, so another point of view of the same problem is we look at it in the so-called the parameter space, right? So in the x-axis here, in the horizontal axis here, that's the parameter value x that we want to find. Every data point AI, BI, you can plot it in this parameter space. So every line here is the residual of a particular point given any candidate X. Okay, so if we have a bunch of points, then we have a bunch of V curves that look like this. So the consensus maximization or the MaxCon problem is we're only willing to tolerate an error of epsilon. That's the so-called inlier threshold. Find me the X such that as many of the points as many of the V curves lie below the line epsilon as possible. Okay, so for example, if my X is here, then I count that there are exactly 3 points or 3 V curves that lie below epsilon in this X, and therefore the number of inliers is 3 in that example. All right, so a quick definition of a particular robust formulation. What does it mean when we say we want global optimality? That means that we want to find the model M star or the model parameter M star such that no other model has a lower objective value. Okay, has a lower robust objective value. All right, that's what we mean by a global optimal solution. And immediately, because we see that rho, for example, the hard redescenders or that outlier counting objective function that I showed earlier, because they're non-convex, immediately we know that this problem is intractable in general, right? And really there is nothing much to say beyond this point. Remember in Anders's segment, there are two ingredients to make a problem tractable. First, the objective function has to be convex. Second, the optimization domain has to be convex. Okay. In the previous talk by Anders and Luca on relaxation, it was mostly about making the optimization domain convex. The objective function to begin with was convex, so there wasn't much of an issue. But when we have outliers and we want to ignore outliers, we will use hard redescenders. They are non-convex, and that basically means, it's NP-hard to begin with. Some of you would say, but RenSec works well. What are you talking about? Yes, RenSec works well, usually. What is RenSec? Let's recap a bit. In the running problem here, a minimal subset in RenSec, as we all know, RenSec samples, minimal subset. A minimal subset would contain actually just 1 point, because all our lines must pass through the origin. So 1 point is enough to realize a minimal estimate in RenSec. Regardless of the size of the minimal subset, the RenSec algorithm says if you draw this number of samples with probability gamma, you get at least one minimal subset that contains only inliers. Okay, so what is the problem with that? Well, here's an adversarial case for RenSec. Maybe adversarial is the wrong word to use for it, but it's popular these days with deep learning. Adversarial case for RenSec, because why? Why is it an adversarial case? Well, you can see that this is an estimate, with the inlier threshold epsilon that captures all the points in the consensus, in the epsilon band, but that estimate does not pass through any of the points. These are two estimates or two minimal subsets that a RenSec algorithm would sample, but none of them give you, these two don't give you good estimates for that line we want. And if you can try all the other points, other minimal subsets, minimum estimates, none of them will give you good estimates. Okay, so yes, RenSec works well in general, but this talk is about certifiable global optimality for safer robotics. What we worry about is not when RenSec works well. What we worry about is when it doesn't work well, you don't know why. You don't know if it's because you've been unlucky or because there are no good solutions to be found. Personally, to me, and I think with my co-organizers as well for this workshop, that's not a satisfactory solution. When it doesn't work, you don't know why. Okay, so okay, fine. We said it's already non-convex, it's NP-hard. What is there to, what is more to be said about this? Well, I mean, if you dig deeper into it, there are actually interesting results we can make as well. So before we get there, let's look at a problem that's related to RenSec. Eventually will be related to the consensus maximization problem, least median squares. Given the same setup, instead of minimizing the count of outliers, we minimize the median of the residuals. Okay, so geometrically or intuitively, it's find the thinnest slab that encloses half of the points. We can generalize that a bit and says, in the problem called least kth order statistic, LKOS, find the thinnest slab that encloses k of the points. So R in brackets k here means the kth largest residual given candidate X. Okay, so in the previous slide, we just take k as half of n. All right, this is generalizing it, saying k can be any number between 1 and n. So given any candidate X, we sort all the residuals. We find the one that's the kth largest. Okay, and we want to find the X that minimizes the k largest residual. Geometrically, this is finding the thinnest slab that encloses k of the points. Cool. So how does it look like in parameter space, this LKOS? Again, remember that we said earlier, each data point gives rise to a V curve. At any X, we can sort the residuals and we find, let's say, the 7th largest one, right? So for this X here, remember X is a point on the horizontal line, horizontal axis. For this particular X here, we count which is a k largest residual, and it's given by that blue point there, or cyan point there, okay? If we check all possible x's and find the k largest residual, they make up that red line there. Okay, so, you know, take any x, count all your way up until the 7th, it's where that red line is. All right, so that's the objective function, r in brackets 7. Okay, so what are we trying to do here? So let's say we know how to solve LKOS. Okay, let's say if I give you any k, you can always find that cyan point. Okay, you can always find the minimum point on that line there, the red line. If I change different k, you can still do it. Assume that we have a black box algorithm that allows us to do that efficiently. And for k equals to 10, that's where the cyan point is. For k equals to 9, that's where the cyan point is. All right, so let's say we can do that. Now, if we can always do that, then we can use the black box that solves LKOS to solve actually our target problem, which is a consensus maximization problem. Okay, so how do we solve it? Well, we just iterate through k from k equals to n, 10 in this case, and keep reducing. Every time we find a solution of LKOS for that particular k, if that solution is below epsilon, then we stop. Okay, so this is what we do. Again, k equals to 10, find that cyan point. Is it below epsilon? No. K equals to 9, is it below epsilon? No. Is it below epsilon? K equals 8? No. We keep going until it's below epsilon. Then that also actually says, hey, this is the point x where the most number of lines lie below epsilon at that point. Okay, so for this particular problem, we know that we can solve the maximum consensus solution with 6 inliers. All right, so let's flip the problem over. Can I solve LKOS using MaxCon? Assuming we know we have a black box routine that can solve MaxCon, for whatever epsilon we provided, it can always find the line that contains the most number of points in that epsilon slab. So I could, you know, try different epsilons. In fact, I could do bisections, start with a big range for epsilon and keep halving the interval. Every time I have a specific epsilon range, I check in the middle. Can I find a x that contains the most number of inliers, and what is that number? Okay, so I keep going until that number is the number I want for the LKOS, let's say 7, then I would have found the solution. So what this is saying is that if we know how to solve one, we know how to solve the other. If we know how to solve LKOS and MaxCon, if we know how to solve LKOS, we know how to solve MaxCon. If we know how to solve MaxCon, we know how to solve LKOS. So the problems are kind of dual in a different sense that was mentioned in the 2 previous talks. And since we don't have efficient algorithms, polynomial time algorithms for either of them, that means that both of them must be difficult. So that's a hand-wavy, quick way of saying, you know, this is an NP-hard problem, which is not surprising to begin with. As we said, you know, the cost function is non-convex. So we can push this further and say, hey, let's say I solve a different problem first. I'm minimizing the max norm. This is a different name for it, the Chebyshev problem. Find the thinnest slab that encloses all the points. So Anders kind of mentioned this. So this problem is always solvable because now the V curve is equivalent to setting k equals to n for LKOS. And I can always find the global minimum because that top line there is always convex. So I can solve it using a convex routine. And in fact, you can observe other things, interesting things about the solution as well. It's always supported by two V curves here in this one-dimensional problem. So these 2 V curves correspond to 2 active points or what we call the basis of the problem. And in fact, this inlier set that we're looking for, you can also find the basis for it. Okay, so this always exists. which provides us a solution for MaxCon that looks like this. We just simply sample all these active sets. And for linear residuals like this, you can show that the active set is always size d+1. You generally enumerate all of them, and we have an n to the d+1 solution. Okay, there's a poly d there because every time we sample a d+1 subset, we need to solve the Chebyshev problem. So this means that we can solve MaxCon in time. This means that MaxCon is in class XP or slice-wise polynomial, meaning that if you fix the dimension, the problem actually becomes polynomial time solvable. But it doesn't mean that it's easy to solve, because d is actually part of a variable, part of the input size. So it's still exponential, but now we're exploiting the structure of the problem. What we're trying to do here is to push further than that. Can we do better than exponent in D? All right. If it's already in class slice-wise polynomial, we want to ask the question: can we remove the dimension from the exponent, put it in front in an arbitrary function f? Okay. So if that's possible, we would say that MaxCon is in a class fixed parameter tractable. So unfortunately, I'm not going to go through the detail here. It's quite involved. You can show that via an FPT reduction from the click problem to the consensus maximization problem that it's just not possible. And we say that MaxCon is W1 hard in the dimension D, which means that any global solution, even if D is a parameter that you can fix, D must be in the exponent of the runtime of the algorithm. And yeah, this is the W1 hardness result. So this is the start of the bad news. Okay, we're almost okay. This is the start of the bad news. We have more bad news. For this particular formulation of geometric understanding with outliers, consensus maximization, it's NP hard. It cannot be solved in polynomial time, and it's W1 hard in the dimension. Even if you're allowed to use knowledge of the dimension D, D has to be in the exponent of n. And this derivation I'm not showing in this talk because there's not a lot of time, but you can also show that there are no polynomial time approximation algorithms. Okay, you can't have an algorithm that runs in polynomial time where you can be sure from the onset, there are sufficiency conditions that tell you that your result won't be, a bounded error away from the optimal solution. So RANSAC is not an approximation algorithm, by the way, because there are no error bounds. As we mentioned earlier, when it gives you a bad result, you do not know why. You do not know if it's because you were unlucky, you sampled the wrong Miller subsets, or there are no good solutions to be found. And our collaborators have discovered similar results as well. For the minimally trimmed squares formulation of geometric understanding with outliers, for example, instead of just maximizing the number of inliers or minimizing the number of outliers, we want to so here it is minimizing number of outliers. We also check that the inliers, the sum of square of them, are less than or equal to epsilon. So this is the minimally trimmed squares formulation for robust geometric understanding with outliers. And it's also, you can show that there are no quasi-polynomial time algorithms that can find the solution we want that is within a factor lambda from the optimal solution. And these are all robust formulations that have been proposed in the statistical community, and it's provable these are all NP hard. So yeah, bad news, right? So yeah, here's some good news. And I want to show let's see if I can. I'm going to pull up a browser to do that. Let me share again. This is from a different browser. So this is a you know, an industry grade software which we didn't build, but we supplied the algorithm behind this. Cool. So it's essentially in the robotics literature, we would call this scan matching, but you know, it's basically point cloud registration, right? And this is a point cloud processing software suite by a company called MapTech that's headquartered in Adelaide here. They deal a lot with the mining industry, as you can see here. What you're seeing here is a global algorithm, point cloud registration algorithm, running, you know, really efficiently. So we in the research community care a lot about, you know, polynomial time solvable, global optimality and all that. But on the other hand, let's not forget as well that if you have fantastic software engineering, sometimes algorithms that are not provably efficient can run really fast in practice. And yeah, we're about to see another example of globally optimal registration happening. And here they're aligning LiDAR scans from an open pit mine, as you can see. Cool. So it's not all bad news. 6 DOF at least we can still solve quite efficiently if engineered well. Okay, so theoretically though, what can we do? I think Hank will in his talk will mention more recent results that are more optimistic. But before that, let's see what the theory allows and does not allow us to do, right? So in regards to geometric understanding with outliers, we have two extremes. On the left, we have heuristics or randomized algorithms such as RANSEC and variance. On the right, we have globally optimal solutions. The theory says, in practice, we know that the left extreme is very fast usually, the right extreme is very slow. But the theory says that if you want fast, you can't have guarantees. Okay, and if you want globally optimal, it has to be very slow. Okay, that's what the theory says. There's nothing we can do about this. The other thing we can fix is, of course, for a lot of robust algorithms, a lot of them use sampling, and this might be an aspect that we can improve by making them deterministic. So what is in the middle here? You know, our algorithms, we all want fast because our self-driving car needs to operate efficiently. The theory says we can't have guarantees, not global optimality guarantees at least, but at least we can make it deterministic. Okay, so what else? What can we do in regards to that previous plan here, making it deterministic, and also hopefully speed up as much as possible? Three main strategies here. Let me check my time. I think I have 5 minutes left if I use my 35-minute limit and based on my starting point. So I'm gonna just roughly sketch these solutions. The first solution is to exploit the problem structure. And this is ongoing work that we're still doing. So coming back to the V curves again, and looking at these cyan points, zooming in a little bit more. Now, if we solve the L infinity or the max norm problem, it's easy. We know that we can solve it globally optimally because in this example, all our curves are linear anyway, but you can generalize it further and show that this works even when it's pseudo-convex. So we can find that solution, find that green point quite easily. But if we remove it, one of them at least, then we can solve it again as well, recursively, solve it again by removing one point and keep going, okay? So this is not trying to do anything, but to illustrate that actually these cyan points here, you can reach any of them from the top by following a sequence of removals. So all these cyan points lie actually on a tree, and each level of a tree corresponds to the number of points you have removed. you can regard these points as the outliers that you have removed. So by exploiting structure, this is what we mean. If you just run a standard rensec on the bunch of points there, you would think that all these estimates, these minimal estimates, actually lie randomly in the parameter space. But if you look at the how these V-curves are organized, you realize that there's further structure in the data, in particular tree structure. Okay, the points are organized in layers. Actually, I should be more careful. It's not; these are not the data points, but each of these is a active point, an active set, a basis. So the depth of the tree tells you the number of points that's being excluded. Okay, so this red point here, for example, corresponds to that and that point as the active set. And because it's at level 3, it's excluding exactly 3 points. So with this knowledge, we can solve the consensus maximization by searching the tree. So this provides us a structure to work with, all right? So we can restate the problem as finding the active set B that has the lowest possible level as close as possible to the root, and whose height, which is the size of that slab, is below epsilon, and which is when we call feasible. Okay, so we can search it level by level. This is one algorithm, and that will be the breadth first search. We can search it using A-star search with a heuristic. And this is when we get back to the branch and bound idea that Anders mentioned at the start. If you think about it, searching the tree, isolating and pruning the branches is actually similar. It's actually the exactly same idea as branch and bound. Instead of pruning using a bounding function, you prune it using a heuristic, which is really, you know, it can be solved, can be computed using a convex relaxation of you know, a subset of the points, right? So it's the same idea expressed using different knowledge. But what we can do here, though, this way of doing branch and bound allows us to bound the runtime. Okay, we can show that because we don't need to search beyond level O is number of outliers we have, and because we know that the branch-in factor, because each basis has d+1 points, the branch-in factor is therefore is d+1. It allows us to bound the runtime such that, you know, it's only exponential in the dimension d, and also the number of outliers O. Okay, so this would be one solution. The other solution is pre-processing, and I need to speed up here. We try to find a subset of the points that contains inliers only, and we know, you know, that's very difficult to find. This big set here is difficult to find. D is a whole data set of points that we have. We have, you know, we're finding pockets. If we have a heuristic algorithm or suboptimal algorithm, we're finding pockets of these inlier sets. We can never guarantee finding the big one. But what if we change the problem? Instead of trying to find I star, what if we find D prime? Where D prime is a subset of D, but D prime guarantees to contain I star. And this is what we call the pre-processing problem. I don't think I have time to go through this. I'm going to show you the outcome of it. Sorry about that. So in the point cloud registration problem, again, we have a bunch of correspondences computing using a black box. Instead of trying to find those green lines, that I star, the inlier set from the get-go, what if we just remove as many of the red points as possible in a manner that guarantees that none of the green lines are removed? Okay, so this will be what we call the pre-processing step. It actually can be achieved really quickly, like in 4.62 seconds. In this example here, we remove almost all of the correspondences, and then we're left with 60 in a manner that guarantees none of the inliers are removed. Okay, and if we subject this set of remaining points to further optimization, then, you know, it's much faster because there are much fewer points to deal with, much fewer correspondences to deal with, and the outlier rate is also significantly reduced. So sorry, I don't have time to go through this. And convex relaxation, I'm just going to briefly go through this because I know Hank will be covering this as well. One of the previous work that Hank and Luca have done is on 3D corresponding, estimating rotation from 3D correspondences, or so-called Waba's problem. Given a bunch of these correspondences, find the rotation R that minimizes square, sum of square of the errors. If you have outliers, you need to consider a robust norm. In this case, we can consider the truncated least squares norm. And we're trying to find the minimum between the error itself as well as some threshold C, which is squared. And not going to go through the detail, but as before, we're trying to get it to a QC-QP formulation, which is then relaxed. And similar techniques that covered by Luca before, instead of finding R, we find Z, the matrix that multiplies the R's together. And we've removed the rank constraint, hence we get the convex relaxation. And it's provable that it's always tight in noiseless and outlier free case. If you add further constraints, as Hank will show later, it will often lead to certify the optimal solutions in cases with outliers. So these are the three main things we can do under the theory, under the fundamental hardness result. Okay. So I want to spend 1 minute to talk about that last point here. I mentioned at the start of the large part of the talk is on showing what's not possible. And what we found was that with outliers and you use a robust norm, the theory forbids you to do anything. But then how is it consistent with that last point here? We can still get certified of the optimal solutions. The key concept here is sufficiency, right? As Anders mentioned, there are two ways to achieve global optimality. One is to show that there are conditions where it's always possible, and one is to verify after you get the result that it's global optimal. What the hardness result forbids is the first type, the sufficiency, coming up with an algorithm at the onset that says this algorithm runs in polynomial time. It will guarantee you an error within this much. Okay, so that's what the theory forbids. So it's not inconsistent with the result here. And here's a list of references.
Thanks. I love the plots. I think the plots are super insightful. Like, looking at low dimensional problems and try to really look at the search problem, which is solved, like, for these outlier rejection problem. I think it's super insightful. I have a question which goes back to what's possible and what's not possible. Question is the following. So intractability results clearly are showing that in the worst case, there is not much you can do in polynomial time, right? So there are these very unlucky instances in which there is nothing you can do. Are you aware of any result which is looking more at the average case? So, like, maybe we would be happy saying that if this worst case instances happen with probability 0, maybe that's not too bad, right? So are you aware of any result saying that in that sense, like maybe average complexity or like anything else along that line?
Average complexity, no, I'm not aware of. We did run some empirical result to find out, the hardness theory says it's not possible to bound. The worst case bound is bad, but are there instances where how often do these hard instances occur? We ran on the Kitty data set and we discovered that, just estimating for, successive frames, estimating the epipolar geometry, most of the cases are hard, unfortunately.
Okay.
Empirically, yeah. So that kind of reduced our motivation to go further down that track.
that's consistent with the experience that we have on our side. Like, at least if you look at Ransack and so on, that's consistent. When I asked the question, I was thinking also about, I don't know if you're familiar with these results from simplex method used for linear programming. Simplex method is exponential time in the worst case, but there are these nice average complexity results in which everything becomes easier.
Smooth analysis.
That's right.
So smooth analysis is another path we considered before, but yeah, it's not easy to get into, at least for me. So it might be possible, but even without smooth analysis, there's already strong empirical result that simplex is usually polynomial time, right? The smooth analysis kind of confirms that empirical result. What we're facing here is different, though. Most of the time, the empirical result shows that it's not easy. It's not fast.
Yeah, that's
so we did toy with smooth analysis. So I mean, Shub in the chat window mentioned something which is very reasonable and promising. He said, I was wondering what would happen if probabilistic guarantees are sought instead of exact solution. Yes, that is an avenue. That is an avenue. And Shub, if you check an archive paper we published, we submitted or uploaded a couple of weeks back, we were aiming for a quantum solution to this problem. And in finding for that quantum solution, we found a classical algorithm that provides probabilistic guarantees, not in the exact consensus maximization or any of the robust norm that we were talking about. I was talking about in my talk. Different formulations for robust fitting, and classical algorithms can provide probabilistic guarantees, and quantum algorithms can in fact speed it up. So which is why I'd say it's promising avenue.
Very cool. So TJ, thank you so much. And at this point, we'll pass the word to Hank for the final presentation. Hank, feel free to unmute and share screen.
Okay. I'll share my screen. Does everybody see my screen? The slide? Yes. Okay. Okay, yeah, so in this last talk, I'm gonna particularly talk about basically the third point of TJ's strategies in dealing with robust estimation with outlier, which is convex relaxation. And I'm gonna talk about certifiably robust geometric perception with outliers. Basically, so we already know that the theory prohibits us from doing anything that has guarantees a priori. But then we are trying to answer the question that after solving some problem, can we certify or verify if the solution is actually globally optimal? So basically, we want to get a posteriori guarantees from it. So before I talk about the technical details, I still want to kind of motivate the geometric perception and also geometric perception with outliers. Geometric perception is essentially the task of estimating geometric models from all sorts of visual measurements. The model we're trying to estimate can be poses, can be 3D structures, and then the visual measurements can be images or point clouds, as we have already seen in previous talks. And geometric perception spans a whole spectrum of problems. For example, it can be pose estimation, it can be localization and mapping, it can be object detection and 3D reconstruction. And then in robotics, we have geometric perception actually underpinning a bunch of applications. For example, autonomous driving, manipulation, autonomous flight, and also autonomous search and rescue, SLAM, these type of applications. And then, as Luca talked about, over the past few decades, the community has made a tremendous progress in terms of solving geometric perception with optimality guarantees. In particular, an increasing number of so-called non-minimal solvers are being discovered, typically based on convex, semi-definite, and sum of squares relaxations. And the unique feature of these non-minimal solvers is that they not only provide an estimate to a geometric perception problem, but also they provide these optimality guarantees after computing an estimate. So for example, we've seen examples like mesh restoration in the case where we have a clean 3D mesh and then we have a noisy point cloud observation of the mesh. And then given all correct correspondences from the mesh to the point cloud, we have the globally optimal solver proposed by Borealis a few years ago that can compute the globally optimal alignment from the mesh to the noisy point cloud. And then we have shape alignment, which is basically, we are still given a mesh, but now the observation is in 2D, which is just a 2D image of the 3D mesh. And then we're trying to figure out the optimal camera pose when observing the 2D image. And then in this year's ECRA, we proposed a sum of squares based relaxation solver that can actually compute the globally optimal camera pose. And eventually in post-graph optimization, which is the example that Luca helped us walk through in great detail, that the famous SE-Sync solver can actually compute the globally optimal post-graph. But then also, as Luca and TJ hinted, the bad news is, in practice, we always have outliers. And then these non-minimal solvers, since they are designed using usually a least squares estimation framework, they're actually not robust to outliers. For example, if we just spoil a couple of incorrect correspondences in these data association, then these non-minimal solvers will actually struggle a lot in computing an estimate that's actually close to the ground truth. As shown by these images, the estimations provided by the non-minimal solver is actually far away from the ground truth. But then what comes to rescue is that in computer vision and robotics, we have a tool set of outlier robust estimation that can actually handle these outliers with great empirical performance. So for example, from the very classical ransack that TJ talked about, is actually very fast, and usually it gives you an estimate that's actually very accurate. And then more recently in Spark Lab, we proposed ADAPT and GNC, where ADAPT stands for adaptive trimming and GNC stands for graduated non-convexity, that can actually also acts as a general framework to robustify all these non-minimal solvers. So to give you an example, if we actually use GNC together with the non-minimal solvers that I've talked about in the previous slides, then the estimates that we can get is actually very close to the ground truth estimation. So in summary, we can actually regain robustness using these general purpose outlier robust estimation frameworks. But actually, in this talk or in this workshop, what we really care about is optimality guarantees, or basically we want to ask the question, has the solver given me the globally optimal solution? So basically we're trying to tackle or deal with the real demon, which is that we want to provide some sort of performance guarantees to these robust estimation frameworks. And then if you look at these ransack or GNC, then you see that these algorithms typically they perform really well when the outlier rate is below, for example, 80%, and then it starts failing when you have more than 80% outliers. Similarly with ransack, it also performs quite well when the outlier rate is below 60%, and then some failures starts occurring when you have more outliers. And then in these, so then one might ask the question that do these local minima or do these failures really do we really care about these failures in practice? So the answer is usually twofold, right? So on one hand, if we are applying these algorithms to entertainment applications such as AR and VR, then probably you don't really care about these random failures because they don't necessarily give you any results that are actually very catastrophic. But then if you are trying to apply these algorithms to safety critical applications such as autonomous driving or space robotics, then these bad local minima are actually going to translate to catastrophic damages to either human life or the machines that could possibly be really expensive, or it's just we just cannot afford these failures. So then what we propose in this workshop is to use certifiable robust geometric perception with outliers. So in a nutshell, I think these algorithms probably have already existed in the current driving or driving assistant systems. For example, if you drive something like Honda or Toyota, they have these safety packages that if they're gonna steer the wheel for you in the highway, in most cases they can do it correctly. But then when they are not confident of their actions, they will actually signal these red signals, alerts to you, such that you want to take the person might need to take the wheel back, or simply to brake the car when the condition is too dangerous. So, and then to provide to put these certifiable robust geometric perception in the context of modern perception pipelines. In modern perception pipeline, we usually have a front end that does feature extraction and matching. In these days, usually it's a neural network based pipeline. And then they're going to output these putative correspondences between visual measurements, for example, from the 3D mesh to the 2D image. And then in the backend, we're performing some sort of robust geometric perception. These days, it's mostly ransack, adapt, or GNC. These very efficient, but algorithms that do not provide any guarantees. So they're going to give us some sort of estimates. These estimates are most likely going to be correct, but in some rare cases, it does fail, as I showed in the previous plots about the failure rates. But then these, as I also motivated, these rare cases of failures will actually hurt you when you try to apply these algorithms to safety critical applications. So what certifiably robust geometric perception does is that it's going to replace these ransack, adapt, or GNC with some algorithms that can actually certify these estimates. So basically, it will not only compute an estimate, but it also give you a certificate of when the estimate is correct and when the estimate is not correct. And I also want to stress that, also stressed by Luca and TJ. So these certifiably robust algorithms are actually significantly different from these certifiable perception without outliers. As I will show this difference in two soon, they actually differ in two main aspects. So the first main aspect is that in certifiably robust algorithms, we explicitly consider outliers, and then we use a robust cost function that is known to be robust to outliers. And then the second main difference is that when you're trying to relax these problems, it becomes significantly more challenging, and then it requires some more tools from optimization and apply math. So the first difference, as I hinted, we're going to use a robust cost function that's called truncated least squares. And then this robust cost function is going to help us kill the outliers. So as TJ already introduced, geometric perception we can treat geometric perception as a general form of optimization. And then in this optimization, we're trying to estimate the geometric model denoted as X, and then we are given visual measurements denoted as Y. And then we have a residual function. For example, it can be the Euclidean distance in 3D registration, or it can be reprojection error in PMPs, the type of problems. And then we have a cost function that can be either non-robust or robust. In the non-robust case, it's least squares. And then in the robust case, TJ has a plot of all sorts of robust estimation cost functions. So to give you a very simple example to actually to give you an example of this optimization problem in 3D registration, when you have all correct correspondences, we're trying to estimate the scale, translation, and rotation given visual measurements, BI and AI. And we are going to motivate the truncated least squares estimation throughout this talk. And then you will see that this truncated least squares estimation will actually give us benefits when you're trying to optimize it. So first of all, what is truncated least squares estimation? So truncated least squares estimation is essentially to replace this rho function here with the truncated least squares cost function, denoted as this inner minimization between the residuals and a constant threshold C bar square. And then if you look at this inner minimization more closely, then you will realize that when the residual is actually small, which usually means that the corresponding measurement yi is an inlier, then the minimization will prefer the residual function, which is r squared. And then, but on the other hand, when the residual is actually larger than C bar square, which is the constant threshold that we've set, then this outlier will not be penalized. So it will become a constant that will not affect the solution of the optimization. pictorially, the TLS estimation cost function is a truncated least squares. And then the inliers will be mapped to the least squares part. And then the outliers will be mapped to the horizontal constant part. And then, these since outliers are mapped to the quadratic part, it's going to be preserved, and then the outliers will be killed. And as TJ showed, this TLS estimation is theoretically hard to deal with, as can be seen from the non-convex shape of this cost function, and also it's also non-smooth because you have these sharp edges as transitions from the quadratic part to the constant part. And then in the next slide, I'm gonna show the ring that can rule TLS, which is the ring of polynomials. And then we're gonna use polynomial optimization tools to rewrite this TLS optimization problem. And then this TLS estimation framework, as written here, is combinatorial, it's non-convex, and it's hard. And then we're gonna take a closer look at this inner minimization, and we realize that this inner minimization is nothing but a minimization of two scalars, A and B. So the A is just the residual divided by beta I square, and then the B is just C bar square. And then one realized that this minimization of simple minimization of two scalars can be written as a minimization over a binary variable theta. So if you check this right-hand side, when the A is actually smaller than B, this minimization will choose theta to be equal to +1, and then this objective function will recover A. And on the other hand, if the A is actually larger than B, then the minimization will choose B by setting theta to be -1. By using this trick, we're going to rewrite this inner minimization as now a function of the x and y, as well as the thetas that we have introduced. So note that we have introduced one theta for each measurement, yi. So now the optimization becomes binary optimization, which we know that is still combinatorial, non-convex, and hard. But then this comes to the nice feature of TLS framework, which is actually, these thetas are actually, although they're binary, but they can actually be written in a continuous fashion. So, which I will show here that, by enforcing theta to be either +1 or -1 is equivalent to saying that theta I square is equal to 1. So on the left-hand side, this is a combinatorial problem, but on the right-hand side, you actually go back to the continuous optimization land. So this is the first nice thing about this TLS estimation framework. And then one also realized that for common geometric perception problems, the X is usually the rotation matrices or translation vectors. And they usually live in a space X, calligraphic X, that can actually be described using a bunch of polynomial constraints. For example, Luca has shown that R is in the orthogonal group of orthogonal group O3 can be written as R times R transpose equal to 1. And then if you look at that constraint element wise, it's actually just a system of polynomial equations, equalities or inequalities. And then by stacking the X, which is the model that we're trying to estimate, together with the binary variable thetas, which actually will tell you if some measurement is actually inlier or outlier, we're going to rewrite this optimization as a continuous polynomial optimization on decision variables P. So now this is a standard form polynomial optimization. So you might wonder, since we have these double-ended arrows here, so the polynomial optimization is actually equivalently hard as the TLS estimation. Although it's continuous, it's still non-convex and hard to solve. But then, as hinted by Anders and also Luca, the formulation really matters. So now that we have written the TLS estimation in this polynomial optimization framework, we can do something that's very kind of standard in the optimization literature, which is actually to relax and do certification. So to establish these certifiable robust solvers, I'm going to propose or claim that there are actually exactly two ways of designing certifiably robust geometric perceptions. So one way of designing or relax this problem is actually to try to directly tackle the polynomial optimization problem. So what we're gonna do is to relax this non-convex problem to a convex one, which we call convex relaxation. Already talked a lot in the previous talks. And then by solving this convex relaxation, which is usually will becoming a semi-definite programming, you can obtain an estimate, but at the same time you can get a certificate of when the solution is actually the global optimal solution. And then on the other hand, we can actually also leverage existing solvers such as RANSAC or GNC, and then this will goes to the second method of designing certifiable algorithms, which is actually we will directly solve the TLS robust estimation using fast heuristics such as RANSAC, ADAPT, and GNC, which will give us an estimate. And then, but now we're not going to stop here because we care about global optimality. And then what we're going to do is we're going to take these estimates and then we're going to perform certification or verification that will give us return a certificate for this estimate. And then, so this is the high level view of designing certifiable algorithms. More specifically, what are we going to do, or what tools are we going to use to design a convex relaxation and certification of any estimate? So I will introduce, not me, so it already exists in the optimization literature. For convex relaxation, we can use Lassier's hierarchy of moment relaxations, which has great similarity with SCP relaxation or relaxation of QCQPs, but it's a more powerful hammer that can deal with more general polynomial optimization problems. And then for the fast heuristics, which is, we already have them. We have GNC, RANSAC, and ADAPT, all these fast heuristics that performs really well in practice. But then for the certification, we're going to use a different optimization technique called Doppler's restful splitting, which is different, which is different than directly solving an SCP. And then this DRS will actually offer some scalability benefits to our problems, and which I will show in the next few slides. And then what I'm going to stress here is that the certificate is actually a suboptimality gap, which will basically tells you the distance between your estimate and the global optimal solution. And then back to Anders' talk, this gap is also basically the duality gap. Or when the gap is 0, we say that this problem actually has a strong duality. And then for a more fancy view or more precise view of these two lines of designing certifiable algorithms, the convex relaxation is actually the primal perspective, which we relax a non-convex problem directly and we solve a convex problem. And then the dual view is actually doing certification, which is given any result, can we claim something about this estimate? Can we say that this estimate is globally optimal or not globally optimal? So these are really the very high level overview of certifiable robust geometric perception. I'm not going to talk about the technical details of each of these blocks. And later I'll point you to the correct references. But now I'm going to show some promising results of these two lines of research. So the first result I'm going to show is how well does relaxation perform in the presence of outliers. So in here I'm showing a plot where on the x-axis I'm showing an increasing number of outliers, and on the left axis, which is highlighted in blue, I'm showing the rotation estimation error in degrees. And on the right-hand side, on the right axis, I'm showing the relative duality gap. All the you can take it as suboptimality gap of the estimate with respect to global optimal solution. So this problem I'm showing here is called single rotation averaging using the TLS robust cost. So as you can see, this relaxation performs quite well in terms of rotation error. The rotation error is usually below 1 degree, and at most it can be 5 degrees. So it's very accurate. And more importantly, you see that by solving the SDP, we get the relative duality gap. And the duality gap is usually very, very small. It's 10 to the power of -7 or -6 or even smaller. So which means that your solution or your estimate is only a very tiny distance away from the global optimal solution. Or numerically you can take it as 0. So this basically tells you your solution, your estimate is the global optimal estimate. And then I'm showing similar results for shape alignment and mesh registration, which are actually more more complicated applications than single rotation averaging, and you actually encounter these problems in robotic perception. So similar results carry over to these more complex experiments. You see that the rotation error is very tiny, and then the relative duality gap is super small. Although sometimes there does exist cases where when you have a very high outlier rate, the relative duality gap can be non-zero. In this case, in the red circle, I'm showing in a case where you have a duality gap that's 10 to the power of -2, I guess, which is small but not zero. But in that case, you still see that rotation error is actually very small. So basically, the takeaway here is we have achieved tight convex relaxation for a whole spectrum of geometric perception problems. And in these relaxations, we can actually recover the global optimal solution. And you also recover a certificate by looking at the duality gap. And then on the other line of designing certifiable perception is as I showed, which is doing certification. So certification is different than relaxation. Basically, in the certification, you actually have two steps. In the first step, you solve the TLS problem directly using RANSAC or GNC, these heuristics that do not offer you guarantees. And then you're gonna, add another layer of these heuristics to try to give them certificates. So in this case, I'm showing results in two bars of different colors. So in the blue bar, I'm showing results that I run GNC. And since these are synthetic results, synthetic data sets, I know which ones are actually the global optimal solution. So these blue bars showcase that empirically, if I run random runs for 50 times, how many times do GNC or RANSAC give me the correct solution or the global optimal solution? And then the green bar shows that for each of these solutions, can I certify them as correct or incorrect? So you will see that for all the correct solutions, for all the correct estimates, our DRS certification pipeline was able to certify, to provide the correct certificate for these solutions. And then more importantly, when the GNC actually fails, their estimates will not be certified. So this gives you a way of detecting wrong solutions in RANSAC or GNC. And similarly, I'm showing the results of shape alignment or mesh registration. You see that the same results, the beautiful results, carry over to shape alignment and mesh registration. We were able to certify all correct solutions, and we were able to reject all wrong solutions. And as another metric of showing the success of the certification, I'm plotting the suboptimality gap with respect to the iterations of Douglas Rashford splitting, which is DRS. And you'll see that for these correct solutions, the certification was able to drive down the suboptimality gap below 1% or 0.1% really fast, usually within 100 iterations or 1,000 iterations. And on the other hand, when you give an incorrect solution or incorrect estimate to the certification pipeline, the certification the suboptimality gap will actually saturate also very fast. So you see there's this very clear bifurcation of correct solutions and incorrect solutions. So correct solutions will give you a suboptimality gap of below 1% or 0.1%, and then incorrect solutions, its suboptimality will saturate above 10%. So this gives you also a very clear idea of when to accept a solution and when to reject the solution. And then the takeaway here is we were able to certify correct solutions and reject incorrect solutions. And lastly, I want to show the scalability of convex relaxations. So usually people will say that convex relaxations involve solving a large scale STP, and it will not be scalable to real size problems. But here I'm showing that this statement is partially true. So in this table here, I showed the n is number of measurements for each of the previous problems that I talked about, and then this m is the dimension of the STP, and then the t relax is the time that's used to solve the STP directly. For example, using MOSAC, which is a commercial state-of-the-art IP solver for solving STPs. And then the t certify is the time that's needed to perform certification. So basically, I run GNC first, and then I try to certify the solution of GNC. And then SRA, SA, PCR, and MR are just shorthands for 4 different applications. And the double star means that the case is when MOSAC, the SCP solver, runs out of memory. And you see that in when n is very small, which is 20, this is far away from real size problems. You can still solve the SCP, but compare if you don't solve the SCP directly, but you're trying to do the certification of the solution, then you end up with a much faster pipeline that only takes you less than 1 second or a couple of seconds. But then when you goes to larger size problems, when you have, for example, n equal to 50, then you can still solve the SCPs, but it will take you, a few hours or even 1 day to solve this SCP, which no one will do that in practice. But certification can still be run in a reasonable amount of time. Not close to real time, but this is very promising. You see, a reduction of time in probably 1,000 times or faster. And then when we go to n equal to 100, which is a problem of realistic size, the SCPs will basically be not implementable. You just cannot solve it, or you cannot squeeze it into the memory of your computer. But then when you do certification, you can still do it in a couple of minutes or a couple of seconds. So this is really promising, as I see. Certification scales to large problems, and also in certification, we're not completely abandon previous solvers such as RANSAC or GNC. You're actually leveraging their performance. And I'm going to show 2 examples of applying these certifiable perception algorithms to real world applications, such as the first example is satellite pose estimation. Thanks to TJ for providing the data sets. So in the left image, I'm showing a solution that's correct and also certified. And on the right-hand side, you do see that the GNC actually converges to a local minima, which gives you an incorrect estimate. But our certification algorithm was able to declare this as a failure case. So you were able to reject this solution. And in the teaser case, which is a point cloud registration, we show that the teaser can actually run on problems of really large size. In here, on the left video, I'm showing two scans with correspondences obtained from a deep neural network called 3D SmoothNet. It gives you a lot of outliers as shown by these red lines. But then teaser is super robust to these outliers. It can give you a very accurate estimate, and it also will tell you this estimation is correct in the sense of global optimization. And as I'm showing a quote here by someone else running our algorithm, you see that teaser, although it's a handcrafted algorithm without end-to-end learning, people comment that the teaser is really so great. It's at least as good as deep global registration, which is a state-of-the-art deep learning pipeline, which just came out of this year's CVPR. So we are really proud of this work. And eventually, I'm going to show a summary of this recent results. So 3 key things to remember is that first of all, we use the truncated least squares. That's a robust outlier robust estimation that will kill these outliers. And then second is we bring in the tool of polynomial optimization, which is the optimization language for TLS estimation. And then the key thing is that in order to design a certifiable robust pipeline, we need 3 key ingredients. So the first ingredient is that you need to have a tight convex relaxation. In this case, it's the Sears hierarchy. And then we also need a fast heuristics in order to do certification. So imagine that your fast heuristics is just gives you garbage. Then the certification will not do anything, right? Because every time you give it a wrong solution, it will tell you it's wrong. And then this doesn't help for real world performance. So these fast heuristics with very good performances are, from my point of view, are also very important for certifiable perception. And then the last thing is a scalable certification that actually can outperform existing SCP solvers by leveraging the structure of the problem. And then this line here, this picture here, exactly tells you the 2 lines of research. One line is directly doing relaxation, and the second line is we perform fast heuristics, and then we do certification. So in the end, I show you some references and implementation and tutorial that's probably useful for people who are interested in the technical details. So the first reference is the result that just came out, which is like 1 month ago. This probably will be the go-to reference to read if you want to know more about this Lassier hierarchy and its application to geometric perception. And a few other results that in the blue lines, I comment about the keywords of these references. And the last two books, one by Lassier and one by Pablo and Blackerman and Thomas. I think these are two great books that has been the source of inspiration for me to do certified perception. I'll probably recommend these two books if you want to know the 101 of these SDP and polynomial optimization relaxation. And lastly, for some implementation, we have teaser++, we have SCV relaxation, a tutorial from last year's ICCV workshop, and then we have I'll release the Certifiable Robot Perception code very soon on this link. It's currently empty, but it will be populated later. So I think that's it for now. I think I can take any questions.
Thanks, Heng. It was very interesting actually, and these tools are very powerful. I do have questions for you, but maybe let's start with Maulin's questions on the chat. I think he's asking about the what happens if you have false certification? What does that mean, and does it happen in practice?
False certification. Does false certification means that when you have an incorrect solution, you can certify it? I think in that case, yeah, false certification. I can say that if your input to the algorithm is well conditioned or good, which basically means that when you have enough inliers that can define a very good global optimal solution, then it will never happen in practice. But it does happen very rare. For example, when your feature correspondences are simply garbage. When you have a feature correspondences that's all outliers, that doesn't have any inliers, then in that case the global optimal solution is not the ground truth solution that you want. So in the teaser paper we have this concept of what's called an estimation contract, which tells you, theoretically tells you when the global optimal solution is the solution that you want. So false certification, in short, false certification rarely exists, but false certification means that if you can certify the solution, then it already means that the solution is globally optimal. Then the question remains is the globally optimal solution the solution that you want? So false certification will basically means that the global optimal solution is not the solution that you want. Yeah, I'm not sure if this answers the question. I think that's a very important perspective.
It would follow up, if Marin has more questions, invite him to follow up. Maybe one thing that can be useful also for the audience is to, so you were hinting to the fact that with this Lassier hierarchy, with this fancy relaxation, you get all the time zero duality gap, you get essentially strong duality. Can you comment on when this strong duality fails? In these problems with outliers, we know, TJ told us that at some point, some intractability will kick in, so we'll not be able to solve all the problems in polynomial time. Do you have an insight on what is the root cause of when the duality essentially, strong duality fails?
Yeah, that's a very good point. I think from my experience, I think strong duality. So I think I have this intuition that strong duality holds when you have a very strong globally optimal solution. So when I say it, I say a strong globally optimal solution by meaning that this optimal solution is not ambiguous. So we do see that in this for example, when you do mesh registration, right? Usually you just have these point to line and point to plane correspondences. So in that case, the relaxation is actually not tight. But if you add a little bit more information into these correspondences, for example, if you can add the surface normals, estimated normals as an additional registration cues to these problems, then the relaxation will become super tight. So this tiny example gives us the insight that in order to do to have strong duality hold, you want a very unique and a very strong globally optimal solution. So and then on the other hand, if you don't have this strong globally optimal solution, then after solving the relaxation, you'll get a solution that's not rank 1, which basically tells you the solution is ambiguous. You know, the global optimal solution is embedded in this in the solution of the STP, but it's just not so clear because your data is not perfect. So so the perfect data means more visual cues such as surface normals, or it can be more inliers and less outliers. So these are really just I think the intrinsics of this problem. So to design a tight relaxation, you need enough inliers, and you also need very distinguished registration cues, like visual cues, like point-to-point correspondence instead of point-to-plane or point-to-line or point-to-image. So these for example, point to 2D to 3D certifiable perception is more challenging than 3D to 3D. The reason is because from 2D to 3D, the projection actually gives you more ambiguity to this problem. So that's why I think these relaxations can be made tight if you have enough information of the inliers or of the problem, of the ground truth. I think that's my intuition about this.
Thanks. I will stop you here because we have like a few more questions, and I will ask you we have like around 4 or 5 questions. I will ask you to have like, a short reply to each one, if we can. So Shreyash is asking if you can tell a little bit more about the interaction between noise and outliers, and in particular from the TLS, you have 2 hyperparameters. One, I think, is the beta, which is the noise, and the epsilon. And the question, I think, how these hyperparameters are affecting the problem.
Yeah, I see the chats.
Right. And in particular, sensitivity to noise, I guess, is the question.
Okay.
So by the way, do we want to say what is the beta?
So the beta here, beta here is basically the noise. You can take beta here as the, for example, the standard deviation of the noise. And then this C bar square is basically saying how large of a residual above this standard deviation will you consider it as an inlier? For example, 3 sigma, right? So in one dimensional, usually if the noise is a Gaussian distribution, then away from 3 sigma, you will think that this is an outlier. So in that case, you can set beta to be the standard deviation, and you can set C bar square to be 3, for example. Then or 9, then in that case it will. So this is basically the interaction of noise and outliers. So these hyperparameters are not really that sensitive in terms of empirical performance. We found that it performs quite well, within some large range.
I do have a related question from Kasra, with saying focusing on outlier rates can be misleading. From intuition and empirical results, we know that the distribution of outliers influences the hardness. How are you generating your outliers, and how sensitive is the performance of these algorithms on the distribution of outliers? That's a great question.
Yeah, it's a great question. Right now, we're just doing random outliers. Yeah, I agree that when you have adversarial outliers, it's gonna make this problem harder. But we haven't explored it yet. We explored it in the WABA case. We explored it in the WABA case, for example, when you have a bunch of outliers forming another consensus set. Basically, you'll have 2 distinguished rotations that that kind of corresponds to a different part of the data. Then the relaxation will still be tight. It will give you 2 solutions. One solution is corresponding to each of the rotations. So I think it's an untapped regime that to be honest, we haven't explored too much. But I think the relaxation will give you some idea also in that case, in the case of adversarial outliers.
And also, I would say that in the teaser ++ paper, there is some result about which kind of adversarial outliers we can consider.
Oh yes, in the estimation contracts.
That's right. So Kasra is also asking a bunch of good questions, actually. So we discussed a bunch of problems, right? So in most of them, the observation of strong duality is just a posteriori and empirical. for which ones we have essentially guarantees on strong duality a priori. And I think SCCing is something that we mentioned. Rotation averaging is something that we mentioned. Do you want to say a little bit more about the guarantees from Lassera hierarchy?
Yeah. So yeah, a posteriori, a priori guarantees we do have for some of them. You know, for example, for the last year's ICCV paper, the paper that TJ talked about. In that one, we have theoretical guarantees on the case where you don't have you have 0 outliers and 0 noise, and you know it can be extended to the case of small noise. But in these in all the examples that I talked about today, right now the guarantees are purely empirical. But I do believe that some of these problems, you know, you will be able to prove that the strong duality will hold when the noise is kind of is small within some range. Yeah, and also the Lassera hierarchy tells you that if you lift the hierarchy high enough, it's always going to converge. But it's a matter of how if you can implement the hierarchy high enough. Sometimes the hierarchy, when the hierarchy is too high, you cannot solve the STP, so you will not know if the relaxation is tight. But they have theoretical guarantees of when the relaxation will be tight. That when the hierarchy is high enough, it will always be tight.
So the way I see it is that the hierarchy is essentially allowing you to trade off optimality and performance, right? You can decide to have a high level of the hierarchy, you pay the price computationally, but you get an optimal solution. Or you can, like, you know, maybe perform a lower order of the relaxation. You can have faster solution, but maybe you lose a little bit of tightness, right?
Yes, a little bit of the tightness. But you know, the tightness doesn't really matter in terms of, you know, if you were just to do certification, right? If you just want to say when do I accept an answer and when do I reject an answer, as the graph that I showed in the plots, you know, usually the graph are actually very distinguished in terms of incorrect solutions and correct solutions. So when you do certification, this type of even though you don't have very perfect strong duality, it might not necessarily matter.
Okay, I think this is related to the next question. I think that there are good questions, so we'll keep going. There are like probably 3 more questions, so we'll keep going. I know that we are out of time, but you know, I think these are fairly interesting. So related to what you say, Kazra is also asking, with the certification approach that you have, can you provide the suboptimality gap also when you do not have strong duality?
Yes, the certification, I think the first question Kaso asked is regarding does the certification rely on empirical tightness? I think that's definitely yes. So if, you know, in the certification, we are actually certifying the relaxation. We're not certifying the original problem directly. So which means that if you don't have tight relaxation, then the certification will also not going to work. So because they are primal and dual, so they are, you know, 2 sides of the coin. They are highly related. So that's why in the summary, I say that, you know, the three ingredients are actually, they're all necessary. You know, first of all, you need to have a high relaxation. And then from the relaxation, you can develop more scalable solvers. And the second question is, yes, even when you don't have strong duality or tight relaxation, the certification will still give you a suboptimality gap, a valid suboptimality gap. It's always correct. The suboptimality gap is always a bound on the suboptimality, even though you don't have strong duality.
Cool. Okay. So Minsan has a question about, does certification mean checking the duality gap with the global optimal? But did you mention solving the global optimal is prohibitive in terms of time and resources?
Yes, yeah, this is a very good question. I think yes, the answer is the duality gap is between the estimate and the global optimal. But you are correct that the global optimum is unknown. We don't know the global optimum, you know, because the theory prohibits us from knowing computing the true global optimal. But you know, the beautiful theory of Lagrangian duality is that you know, in the certification, you actually don't need to know the ground truth. It's like a sandwich, you know the upper bound and you know the lower bound. If the upper bound and lower bound are close enough, then you know that the global optimal solution is sandwiched between these 2 bounds. So that's why you still get the valid optimality bound, even though you have no idea of the global optimal solution. I think that's the beauty of duality.
Okay, great. I think we'll go for the last question. Matt is asking, first of all, he's commenting that that's an awesome, very general approach. He's asking if you tested these on problems like SLAM or rotation averaging, where the decision variable size grows with the number of measurements. And in that case, if you can use sparsity, or maybe assuming that just a subset of the measurements are outliers, can you make the certification tractable? I think that's another great question.
Yes, so I think yes. If you look at the paper, we do use the sparse version of sum of squares relaxation. This is more technical, but I think Matt will be able to understand that. So in order to do the certification, so the certification is the first order method. So you know, first order method although it's a convex problem, but its convergence will depend on the initial guess. So the initial guess is actually obtained from solving a sparse SOS program. So that initial guess actually bootstrapped the convergence of certification. So I can safely say that without that scalable sum of squares, sparse sum of squares, we will not be able to achieve this amazing scalability of certification. So I do see that sparsity can help a lot in these problems. But on the other hand, sparsity is not enough. So if you just purely rely on sparsity, for example, if you directly do a sparse Garcia hierarchy, is not going to be tight. So that's the takeaway of this. But you know, from again, duality helps. Duality helps. And although you have a non-tight relaxation from the sparse SOS, but you can actually utilize that as an initial guess for a more powerful relaxation, which is dense but can be solved using first order methods. I don't know if that's.
We'll get a scalable, you know, we'll get scalable to a level in which you can solve SLAM and rotation averaging.
I doubt it. It's still going to be the current state of the art of STB solvers. I think it's still going to be on the order of seconds. I think, not milliseconds. So probably will not be real time, but I think it's reasonable.
All right, thank you so much. I think we are going to wrap up. I wanted to show just a final slide to just wrap up. You should see my screen at this point. The final slide, like, you know, first of all, to thank you all, thank the attendees for the patience and, like, you know, for staying a little bit longer attending this tutorial. Wanted to thank the organizer for giving, like, you know, very insightful talks and sharing their experience with global optimization. So in summary, I think this tutorial is really about 4 points, really. Like, you know, optimization is a key to robot perception and vision. Suboptimal solutions in many cases is the same as unreliable estimates, which is a problem for safety critical applications. And this is one of the first events that we organized around this idea of certifiable algorithms, which are about solving this optimization problem arising in robot perception and certifying optimality, or detecting failure or suboptimality in the worst case. And I hope that out of this tutorial, you got the point that there are many open problems. There are open problems on the theory side, designing new algorithms. If you want to help us, like, you know, also look on, you know, develop very fast implementations to make this run in milliseconds instead of seconds, and even just applying these to common problems, right? So we have a number of online resources. Hank was pointing to some of them. I would say that we kept the RSS tutorial website minimal because, you know, this was embedded on the RSS portal. We could not add much more, but you will find even more resources in the ICCV 2019 website. You'll find the slides, you will find starter code in MATLAB, and we're going to keep a list of references of non-minimal solvers in vision and robotics, and we'll keep that updated. So I want to close with a final message saying, like, you know, if you're interested in these topics, please, you know, help us and just reach out if you have questions. Feel free to reach out to any of the organizers and ask your questions. With this, thanks again to the attendees. Thanks, TJ. Thanks, Anders. Thanks, Hank. And see you guys at the other events for RSS.
Thank you.
Thank you, Luca.
Bye, everyone.
Someone is asking if the recording will be available. I think the answer is yes, right?
Right. Yeah, I'm recording these, and we'll release a YouTube recording of the event as well. Thanks. Great point.